Picture this. The Earth is thawing. For thousands of years, the ice that buried half the Northern Hemisphere has been retreating. Glaciers that once stood taller than modern skyscrapers are melting back. Forests are creeping into land that used to be frozen tundra. Animals are migrating into new territory. The planet is doing exactly what it's supposed to do at the end of an ice age. It's warming up. Life is returning. And then, seemingly out of nowhere, it all reverses. Temperatures crash. Not slowly, not gradually over centuries the way you'd expect from normal climate shifts, but fast. Some estimates suggest parts of the Northern Hemisphere could have dropped by as much as 10 degrees Celsius in a matter of decades. Maybe even faster than that. Glaciers that had been retreating suddenly start advancing again. Forests die back. The warming trend that had been building for thousands of years just stops and slams into reverse. Imagine spring arriving early, the snow melting, flowers blooming, and then winter comes roaring back overnight and stays for over 1,000 years. This is real. This actually happened. Scientists call it the Younger Dryas, and it's one of the strangest, most abrupt climate events in Earth's entire history. But here's what makes it so fascinating and honestly a little unsettling. This wasn't just a footnote in some geology textbook. This event happened right when human civilization was on the edge of transformation. Right when our ancestors were beginning to settle down, experiment with agriculture, build the first complex societies. And it happened at a time that lines up, at least loosely, with some of the oldest stories humanity has ever told. Stories about floods that drowned the world, stories about fire falling from the sky, stories about darkness and cold and catastrophe. So here's the question we're going to dig into. Is there something real behind these ancient catastrophe stories? Could a documented climate shock, something we can actually measure in ice cores and ocean sediment and fossil records, be the seed that grew into myths passed down for thousands of years? Or are we just seeing patterns that aren't really there, connecting dots that don't actually connect? Now, I want to be upfront with you. The Younger Dryas is not some neat, tidy, single disaster story with a clear beginning, middle and end that all scientists agree on. It's messy, it's debated. There are competing theories about what caused it, how it started, why it lasted as long as it did, and how it ended. Some of what we're going to cover is about as solid as science gets. Ice cores don't lie about temperature. Sediment layers don't lie about time. But some of what we're going to cover is genuinely controversial, hypotheses that respected scientists disagree about, evidence that's been challenged and re-examined and argued over in academic journals for decades. We're going to walk through all of it, the frozen archives buried in Greenland and Antarctica that recorded this event ice layer by ice layer, the massive lake that may have unleashed a wall of freshwater into the North Atlantic and shut down entire ocean currents, the extinction of giant animals that had survived ice ages before but couldn't survive this one, the archaeological cultures that vanished right when this cold snap began. And yes, we're going to look at the flood myths, the fire from the sky stories, the ancient traditions that some researchers believe might be echoes of this exact moment in time. Before we go further, tell me where you're listening from and what time it is right now where you are. I love reading these comments. Half the world's asleep, while the other half's just waking up, and somehow we're all here together in this same story. And if you're enjoying these deep dives, the best way to support what we do here is to follow the show on Spotify. Listen there, and if you've got a minute, leave a 5-star review. It genuinely helps more than you'd think. Links in the description. Now, let's go back nearly 13,000 years, to a world that thought the Ice Age was finally over. So let's set the scene properly, because to understand how strange the Younger Dryas really was, you have to understand what the world looked like right before it hit. Around 15,000 years ago, the planet was in the final act of the last great ice age. And when we say ice age, we're talking about something almost impossible to picture from where we're sitting now. Ice sheets over North America, the Laurentide ice sheet, were piled up nearly 2 miles thick in places. 2 miles of solid ice sitting on top of what is now Canada and the northern United States. Another massive ice sheet, the Scandinavian ice sheet, buried northern Europe under similar conditions, stretching across what's now Scandinavia, the Baltic, and deep into Russia. Sea levels were roughly 120 meters lower than they are today, because all that water wasn't in the oceans. It was locked up as ice, sitting on land, reshaping the entire geography of the planet. Think about what that actually means. Places that are underwater today, the English Channel, large parts of the Bering Strait, huge stretches of what's now the continental shelf around the world, were dry land. You could walk from Siberia to Alaska. You could walk from mainland Southeast Asia out to islands that are now separated by open ocean. The map of the world that we take for granted, the coastlines, the islands, the shape of the continents, none of that existed yet. It was a completely different planet, geographically speaking. But by around 15,000 years ago, that world was starting to change. The ice sheets that had dominated the Northern Hemisphere for tens of thousands of years were retreating. Not overnight, but steadily, year after year, decade after decade. Temperatures were climbing, glaciers were shrinking back, and as the ice retreated, it left behind a landscape in flux. Meltwater rivers carved through what used to be solid ice. Massive lakes formed at the edges of the retreating ice sheets, some of them larger than anything that exists on Earth today. Forests began creeping northward into land that had been frozen tundra for millennia. Grasslands expanded, animal populations that had been squeezed into shrinking refuges during the coldest part of the Ice Age started spreading back out across newly available territory. And human beings were right there in the middle of all of it. This was the world our ancestors were moving through. Groups of hunter-gatherers were expanding into Europe, into Asia, into the Americas, following the retreating ice, following the animals, following the changing landscape. Some of the very first people to cross into the Americas were likely making that journey during this exact window, walking or paddling along corridors of land and coastline that would disappear under rising seas within just a few thousand years. It's a strange thing to think about, that some of humanity's most important migrations happened across land bridges and coastal routes that don't even exist anymore. They're underwater now, erased by the same climate recovery that was supposed to be good news. And here's the thing. The animals of this world were nothing like what we see today. This was the age of the megafauna giant creatures that had survived the harshest parts of the Ice Age and were now living through its ending. Woolly mammoths still roamed across Siberia and North America. Giant ground sloths, some of them as big as elephants, moved through the forests of the Americas. Saber-toothed cats hunted alongside dire wolves. Giant short-faced bears, the largest land predators of their time, prowled across landscapes now flush with returning grasslands and prey. Woolly rhinoceroses grazed across Eurasia. This was a planet still populated by creatures so large and so strange that if you saw them today you'd think you'd stepped into some kind of fantasy world. Now, here's where we need to be really precise about something, because it matters a lot for understanding what comes next. An ice age and a rapid climate shift within an ice age are two very different things, and people often confuse them. An ice age, the big picture, glaciers covering huge parts of the planet, is a slow process. It builds up and winds down over tens of thousands of years, driven by things like changes in Earth's orbit, its tilt, its wobble, the slow cycles that control how much solar energy hits different parts of the planet at different times of year. That's climate change on a geological timescale. Gradual, predictable in its broad strokes, even if the details are complicated. But within that long, slow arc, the climate system doesn't always behave smoothly. And by around 15,000 to 13,000 years ago, the tail end of the Ice Age was actually turning out to be surprisingly unstable. There were already warming pulses and cold snaps happening in rapid succession, some of them lasting only a few centuries, some even less. Scientists have names for some of these earlier wobbles, like the Bolling-Olerode warming period, a stretch of rapid warming that came right before the Younger Dryas hit. The climate system at the end of the Ice Age wasn't gliding gently toward modern conditions. It was lurching, it was unstable. It was in some ways primed for exactly the kind of sudden reversal we're about to get into. And a huge part of why it was so unstable comes down to one thing: water. Specifically, what was happening in the North Atlantic Ocean. The North Atlantic isn't just any patch of ocean. It's home to one of the most important pieces of Earth's climate machinery, a system of ocean currents that acts like a conveyor belt, moving warm water up from the tropics toward the Arctic, and moving cold water back down at depth. This circulation is a major reason why places like Western Europe are as mild as they are, despite sitting at latitudes that should honestly be a lot colder. Disrupt that conveyor belt, even temporarily, and you don't just get a slightly colder winter somewhere. You can flip entire regional climate systems. And at the end of the Ice Age, with ice sheets retreating and enormous amounts of fresh water pooling up at their edges, all of that meltwater was sitting right next to the very ocean system that regulated the climate of half the hemisphere. It was, in a very real sense, a loaded gun. Nobody knew it yet. Nobody could have known it yet. But the pieces were all in place: the melting ice, the shifting currents, the unstable climate, the growing human populations following herds across a changing world. All that was missing was the trigger. Nobody knew it yet, of course. The people living through this change had no thermometers, no weather stations, no way to measure ocean currents or chart the retreat of ice sheets. They only knew that the world their parents had described was changing. Forests advancing, animals moving, rivers shifting, coastlines creeping inland. Then, in places across northern Europe, the cold came back. But it took thousands of years before anyone could see the evidence clearly. And when scientists finally recognized it, they didn't find the first clue in a glacier or at the bottom of the Atlantic Ocean. They found it in mud, lake mud, specifically, layer after layer of sediment that had settled quietly on the bottoms of lakes in Denmark, Germany, Sweden, and across northern Europe. Every year, tiny particles washed in from the surrounding landscape. Dust, clay, fragments of leaves, microscopic algae, volcanic ash, and perhaps most important of all, pollen. Pollen is one of nature's most stubborn little time capsules. Plants release it in enormous quantities, and much of it ends up in lakes and bogs, where it gets buried in oxygen, poor sediments, and can survive for thousands, sometimes tens of thousands of years. Under a microscope, different kinds of pollen have distinctive shapes: spiky, smooth, round, oval, ridged. If you take a core from the bottom of an ancient lake, you're basically extracting a vertical timeline of the vegetation that grew around it. At the bottom are the oldest layers. As you move upward, the sediment gets younger. And by counting, identifying and dating the pollen grains in each layer, scientists can reconstruct entire vanished landscapes. They can see forests spreading as temperatures rise, birch and pine moving north, grasses expanding across open ground. They can see the fingerprints of drought, floods, farming, fire, even human land clearance. But in the sediments from the end of the last ice age, researchers saw something especially strange. For a while, the pollen record showed a warming world. Trees were returning to northern Europe after the coldest part of the Ice Age. Landscapes that had been bleak tundra began supporting shrubs, then woodland. It looked exactly like what you would expect as glaciers retreated and the planet moved toward a warmer climate. Then that trend suddenly reversed. The tree pollen dropped, cold-adapted plants returned, and among them was one flower in particular, a tiny Arctic alpine plant called Dryas octopetala, sometimes known as mountain avens. It has white petals, yellow centres, and a remarkable ability to grow in cold, harsh, exposed landscapes where forests cannot survive. Today you find it in high mountains and Arctic regions. But its pollen and plant remains showed up in abundance in ancient European sediments at a time when the climate was supposed to have been warming. It was like finding evidence that the Arctic had briefly marched back south. This cold interval was eventually named after that flower. Dryas for the plant, Younger because scientists had already recognized an earlier cold phase in the late Ice Age called the Older Dryas. That distinction matters. The end of the Ice Age was not one simple, smooth climb from frozen conditions to the relatively warm world we know today. It had pulses, hesitations, warming periods interrupted by renewed cold. The Older Dryas was one of those earlier cold reversals, occurring before a warmer phase known as the Bolling-Olla Road. The Younger Dryas came later, after that warming had already allowed forests and animals and human populations to expand into newly opened territory. So the name does not mean this was the only Dryas event. It means it was the later, more dramatic return of cold recognized in the European record. At first, this was a regional botanical mystery. Scientists looking at Danish bogs and European lakes could tell that vegetation had changed. The landscape had gone from cold tundra to warming woodland, then back toward tundra again. But pollen alone could not immediately answer the biggest questions. How cold had it become? How fast had it happened? Did this reversal affect only northern Europe? Or was it part of something much larger? And perhaps most importantly, what could possibly make a warming planet turn sharply cold again? The lake's sediments offered more than pollen. In many locations, the layers themselves changed. Warmer conditions supported more vegetation, more stable soils, different kinds of algae, different rates of organic material accumulating in lakes. Colder conditions altered erosion, runoff, lake chemistry, and the types of microscopic organisms living in the water. Some sediment sequences recorded an environmental shift so clear that you can almost read it like a sentence. Forest, warming, stability. Then suddenly open ground, wind-blown dust, cold-adapted plants, and a landscape under stress. The signal appeared in lake after lake, not perfectly identical, because every region has its own geography, rainfall, soils, and local ecology. But the broad pattern kept returning. Warming had begun. Then the cold returned. Then later the warming resumed. That was the first outline of the Younger Dryas, a strange climatic relapse near the end of the Ice Age, preserved in the pollen of a small flower. But the real revolution came decades later, when researchers began drilling deep into the Greenland ice sheet. An ice sheet is not just frozen water, it is an archive. Snow falls year after year, gets compressed into ice, and traps tiny bubbles of ancient atmosphere along with dust, sea salt, volcanic particles, and chemical signatures of temperature. The deeper you drill, the farther back in time you go. In Greenland, scientists drilled through more than 2 miles of ice, recovering cores that reached deep into the last ice age. And there, locked inside the ice, was confirmation that the European lake records had been pointing to something real. The Greenland cores showed a major return to cold conditions beginning around 12,900 years ago. Not gradually over many millennia, not as a vague decline that took countless human generations to notice. In the ice core record, the shift was startlingly sharp. Temperatures in Greenland appear to have dropped dramatically over a period that may have been as short as decades in some interpretations, though the exact pace varied by region and remains an active area of research. That is what made the Younger Dryas so important. It wasn't merely cold. Ice ages had cold periods all the time. It was abrupt. For a long time, people assumed climate changed slowly because the forces driving it, orbital cycles, shifting continents, changing ice sheets, operate over vast stretches of time. The Younger Dryas showed that the climate system also has thresholds. Push certain parts of it hard enough, and it can reorganize fast. The Greenland ice cores gave the event a precise backbone. Then other archives began filling out the picture. Ocean sediments from the North Atlantic recorded changes in sea surface temperatures and ice rafting. Cave deposits preserved shifts in rainfall patterns. Lake records from Europe and North America showed ecological disruption. Glacier advances in some mountain regions suggested renewed cooling. Pollen records showed forests retreating and tundra returning. Different archives, different continents, different methods. But increasingly, they told versions of the same story. The strongest cooling was centered around the North Atlantic and northern parts of the hemisphere. The effects were not uniform everywhere. Some regions became colder, some drier, some wetter, and some responded in more complicated ways. The southern hemisphere did not simply mirror the north at the exact same moment. Climate never works with that kind of neat symmetry. But the evidence made one thing very difficult to deny. Near the end of the last ice age, Earth experienced a major and rapid climate disruption, and the Younger Dryas became central to paleoclimate research because it was a natural experiment on a planetary scale. Here was a time when a warming world suddenly flipped back toward glacial conditions. Here was a chance to ask how ice sheets, oceans, atmosphere, sea ice, rainfall ecosystems, and human societies interact when the system is shoved out of balance. It became one of the clearest examples that climate does not always change at the speed we expect. Sometimes it creeps, sometimes it lurches, and once scientists realized the Younger Dryas was real, the next question became impossible to avoid. What happened around 12,900 years ago that could make the Northern Hemisphere turn cold so suddenly? Around 12,900 years ago, the climate system appears to have crossed one of those thresholds. The exact date depends on which timescale you use and which archive you're looking at. Scientists often place the beginning of the Younger Dryas at roughly 12,900 years before present, with present conventionally meaning the year 1950. It lasted for about 1,200 years, ending around 11,700 years ago, as the planet entered the relatively warm Holocene epoch, the climatic chapter we are still living in today. 12 centuries might sound like a long time, and for a human life it absolutely is. Entire civilizations can rise and disappear in a fraction of that span. But in geological terms, 1,200 years is a blink, a thin line in a deep ice core, a narrow band in a lake bed. The kind of event that from far enough away looks almost instantaneous. And the beginning is what makes it so unsettling. When scientists call the Younger Dryas abrupt, they do not necessarily mean that every place on Earth froze overnight. They do not mean every winter suddenly became harsher on the same day, or that a single storm swept across the world and changed everything by morning. Climate is too large, too interconnected, and too regionally complicated for that. Abrupt means fast compared with the normal pace of major natural climate change. Think about the forces usually associated with the coming and going of ice ages. Earth's orbit shifts gradually, the tilt of its axis changes gradually. Ice sheets build and melt over thousands of years. Forests migrate over generations. Sea levels rise and fall across immense spans of time. These are usually slow-moving processes, operating at the pace of centuries and millennia. But the Younger Dryas onset, especially in the Greenland record, looks different. It looks less like a gentle slope and more like a step. For thousands of years before it began, the Northern Hemisphere had been warming after the last glacial maximum, the coldest phase of the last ice age. Massive ice sheets were retreating. Sea levels were rising. Plants and animals were moving into landscapes that had been locked under ice, tundra, or cold, dry grassland. Then, in Greenland, the chemical fingerprint of the snow changed sharply. That fingerprint comes from oxygen isotopes. Now, an isotope is simply a version of an element with a different number of neutrons. Oxygen has several naturally occurring isotopes, but the two that matter most in ice core climate records are oxygen-16 and oxygen-18. Oxygen-16 is lighter, oxygen-18 is heavier, and as water evaporates, condenses, falls as snow, and moves through the atmosphere, those lighter and heavier forms get sorted in slightly different ways. In colder conditions, snow reaching Greenland tends to contain relatively less oxygen-18. In warmer conditions, it tends to contain more. It is not a perfect thermometer. The relationship can be influenced by storm tracks, seasonality, where moisture came from, and changes in the atmosphere. But when researchers measure these isotope ratios layer by layer through an ice core, they can reconstruct a powerful record of changing conditions over time. And near the start of the Younger Dryas, the Greenland oxygen isotope signal plunges. It is one of the most famous drops in all of paleoclimate science. The ice does not tell us that every corner of Greenland cooled by one exact number of degrees at one exact moment. That would be pretending the record is more precise than it is. But the scale of the shift is unmistakable. Greenland became dramatically colder. Estimates of local temperature change vary depending on the method used, but some reconstructions suggest winter conditions may have cooled by well over 10 degrees Celsius in parts of Greenland, with annual average cooling also severe. That is an enormous change. Imagine a climate that has been moving toward warmer conditions for generations. Snow seasons shortening, glaciers withdrawing, growing seasons expanding. Then, within a span that may have been only decades in Greenland, the whole pattern changes. Winters become longer and harder. Summer warmth weakens. Sea ice expands. The familiar rhythms of the year no longer behave the way they did. For people living in the northern parts of the world, this would not have been an abstract climate statistic. It would have meant changes in the movement of animals, the reliability of rivers, the location of forests, the length of the hunting season, and the basic question of where food could still be found. But here's where the story gets more complicated and more interesting. Greenland is not the whole planet. The Greenland ice cores offer an extraordinarily detailed view of conditions over the North Atlantic region. They are among the best climate archives we have. But they are not a global weather report. The Younger Dryas was strongest in the North Atlantic and across much of the Northern Hemisphere, particularly in regions connected to the Atlantic Ocean, expanding sea ice and the enormous ice sheets that still covered much of North America and Northern Europe. Elsewhere, the pattern could look very different. Some areas experienced clear cooling. Others became drier. Some regions saw changes in rainfall more than temperature. In certain places, ecosystems shifted dramatically, even if average temperatures did not crash in exactly the same way they did in Greenland. Monsoon systems responded, wind patterns changed, dust moved differently through the atmosphere. Lakes rose in some regions and shrank in others. And south of the equator, the timing could be offset or muted. The Southern Hemisphere did not simply flip into an identical Younger Dryas at the same instant. Oceans transport heat slowly, atmospheric circulation redistributes it unevenly. A major disruption in the North Atlantic can send consequences around the planet, but those consequences do not arrive everywhere with the same force or on the same schedule. Picture the climate system not as a single thermostat on a wall, but as a planet-wide network of conveyor belts, engines, reservoirs, and feedback loops. The North Atlantic is one major part of that machine. If it changes suddenly, the rest of the system responds, but the response can be delayed, distorted, or even reversed depending on where you are standing. That is why scientists are careful with phrases like global cooling event. The Younger Dryas was a major climate reversal with wide-reaching consequences, but its most dramatic signature was regional. It hit the North Atlantic world especially hard. To someone in Greenland or Northern Europe, it may have felt like the Ice Age had returned. To someone thousands of miles away, the same event may have appeared as a shift in rainfall, a failing monsoon, altered river systems, changing vegetation, or a disruption in seasonal winds. Even the date, 12,900 years ago, needs to be understood as an approximation. That might sound surprising. We are talking about ice cores with annual layers, chemical measurements of astonishing precision, and dating methods capable of reaching deep into the past. Surely we should be able to point to one specific year and say, there, that was the moment. Sometimes, in the best Greenland records, scientists can get remarkably close. Annual layers can be counted in parts of the core, much like tree rings. Volcanic ash layers and chemical signals can help link one archive to another. Radiocarbon dating provides additional anchors, but no ancient timeline is perfect. Layers can thin under the immense weight of ice. Sections can be disturbed. One record may be dated in calendar years, another in radiocarbon years, and another by matching patterns to a different core. Then there is the basic problem of synchronization. A sudden change recorded in Greenland may not show up in a European lake sediment at precisely the same apparent date, not because one record is wrong, but because sediment accumulates differently, local conditions vary, and every dating method carries uncertainty. So when researchers say the Younger Dryas began around 12,900 years ago, they are not claiming supernatural precision. They are identifying a narrow window in deep time, when multiple records show the climate system changing rapidly. The important point is not whether the first shift occurred in one exact year, or a few decades earlier or later. The important point is that, against the vast scale of geological history, it happened fast. Fast enough that forests could not simply migrate at their own pace. Fast enough that animal ranges were disrupted. Fast enough that human groups whose parents had known a warming world may have found themselves adapting to renewed cold. And this was not just a drop in temperature. A colder North Atlantic changes the entire map of opportunity across the Northern Hemisphere. It changes where moisture goes, where sea ice forms, how storms travel, which landscapes support grassland, forest, or tundra, which rivers remain dependable, which animals thrive, and which begin to disappear. The cold was the first signal, but it was only the beginning of the upheaval. To understand what the Younger Dryas did, forget the idea of temperature as one number on a chart. A few degrees colder sounds manageable. Put on another layer. Build a better shelter. Hunt something with thicker fur. But climate does not work that way. A shift of a few degrees in average temperature can mean the difference between rain and snow, between a river that floods every spring and a river locked beneath ice for months longer than before, between open woodland where deer can feed, dry grassland where bison can graze, and treeless tundra where only the hardiest plants survive. It can change the map without moving a single border. Across much of the North Atlantic world, the Younger Dryas brought a return to colder conditions after the earlier warming had begun pulling the planet out of the Ice Age. Glaciers that had been retreating did not simply pause. In some mountain regions they advanced again, pushing fresh ridges of rock and sediment ahead of their ice fronts. These ridges, called moraines, are still visible in parts of Europe and North America. They are physical evidence that the warming world had reversed course, at least for a time. Imagine living beside a valley where the ice has been withdrawing for generations. Every year, more ground appears. New plants take root in the exposed soil. Animals move into the widening corridors between the glacier and the hills. Then the cold returns. Snow lingers later into spring. Summers weaken. The glacier stops shrinking, and eventually it begins creeping forward again. Not like a wall racing across the land. Glaciers move slowly, but they move relentlessly. A few meters in a year, sometimes more, enough that over generations the landscape people thought was opening up could begin closing again. In Northern Europe, plant communities shifted toward colder, more open environments. Forest expansion slowed or reversed in many places. Birch and pine retreated from areas where they had begun to establish themselves. Tundra plants and cold-adapted grasslands spread again. In the archaeological and pollen records, it can look like the landscape took a step backward toward the Ice Age. That matters because vegetation is the foundation of everything else. Change the plants, and you change the insects. Change the insects, and you change the birds. Change the grasslands and shrubs, and the herds move. Reindeer follow one set of conditions, elk and red deer prefer another. Wild horses, bison, mammoths, and smaller grazing animals depend on particular combinations of grass, water, shelter, and seasonal access to food. Humans do not need to be hit by a glacier to feel a climate reversal. They only need the animals to stop arriving where they used to arrive. A hunting ground can fail because a migration route shifts 50 miles north. A fishing site can become unreliable because a lake freezes longer. Its water level changes or its outlet is blocked by ice and sediment. A valley that once offered berries, game, wood, and fresh water can become colder, drier, windier, and less predictable within a handful of lifetimes. And predictability may have been the real prize. People at the end of the Ice Age were not passive victims wandering through an empty wilderness. They knew their territories in extraordinary detail. They knew when salmon or other fish ran, where herds crossed rivers, which wetlands produced waterfowl eggs, which slopes caught early spring sun, which plants could be harvested before winter. Survival depended on a mental calendar built from the repeating patterns of the year. The Younger Dryas interfered with that calendar. Spring might arrive later. Summer rains might weaken. Autumn storms might shift direction. Winter snow cover could last longer, making travel harder and burying the plants that grazing animals depended on. A resource that had been reliable for generations could become unreliable, not because it vanished completely, but because it appeared at the wrong time. And timing is everything when you are living season to season. The storm tracks changed too. The North Atlantic is one of the great weather-making regions of the planet. Temperature differences between ocean, land, sea ice, and ice sheets help steer winds and storms. When the North Atlantic cooled and sea ice expanded, the pathways followed by storms could shift. That meant some areas likely received less moisture, while others became wetter or experienced more intense seasonal variation. This is why there is no single Younger Dryas weather report. In one region, colder conditions may have meant longer winters and glacier advance. In another, the larger problem may have been drought. In another, Rainfall patterns changed enough to transform wetlands, lakes, and river floodplains. Some landscapes became more open and dry. Others saw lakes rise as changing precipitation, reduced evaporation, or altered drainage trapped more water on the land. A lake is not just a lake in this story, it is a climate instrument. Lakes respond to the balance between rain, snowmelt, evaporation, groundwater, and drainage. If that balance changes, shorelines move. A shallow lake can shrink into marshland. A basin can fill and spill into a new channel. Rivers can cut deeper, spread wider, freeze differently, or carry huge pulses of sediment from unstable slopes and melting ice. For animals and people, these are not minor adjustments. Water determines where game gathers. It determines where plants grow. It determines which routes can be crossed and which become barriers. It determines whether a familiar camp remains beside a dependable shoreline or ends up stranded far from the water that once sustained it. And in a world still shaped by enormous ice sheets, the changes could be especially dramatic. North America was not one uniform continent. Much of the north remained under or near the influence of the Laurentide ice sheet, a vast mass of ice that covered much of Canada and extended into parts of the present-day United States. Its southern margins shaped rivers, lakes, winds, and ecosystems over an immense area. Europe was also still living in the shadow of retreating ice, especially across Scandinavia and the North Atlantic margins. These ice sheets did more than sit there like frozen mountains. They changed the atmosphere around them. They reflected sunlight. They cooled nearby air. They influenced where storms formed and where moisture fell. And as glaciers advanced or retreated, they rerouted water across entire regions. So a climate reversal in the Northern Hemisphere was never only about colder air. It was about moving ice, changing seas, redirected storms, displaced vegetation, altered migration routes, and broken seasonal expectations. It was about the entire ecological web being pulled tight, then rearranged. But we need to be careful here. The Younger Dryas did not transform every place in the same way. Greenland gives us the sharpest and most dramatic signal, but Greenland was sitting close to the centre of the North Atlantic disruption. Its ice cores record a severe return to cold. Other regions show a more mixed picture. Some records are clear, some are messy. Some appear to respond later, or mainly through changes in moisture rather than temperature. That is not a weakness in the evidence. It is what we should expect from a complicated climate system. Think of a giant pond when a stone hits the water. Near the impact, the disturbance is violent. Farther away, the ripples are weaker, delayed, redirected by the shoreline, or interrupted by other waves. The Younger Dryas was something like that, except the pond was the entire climate system. The stone was a major disruption in the North Atlantic, and the ripples crossed oceans, mountains, ice sheets, forests, and deserts. For people in the northern world, the result was not necessarily one sudden moment of universal catastrophe. It was something more difficult to live through, a world becoming unreliable. The land still had animals, rivers still flowed, plants still grew. But the old patterns no longer held, and when a society survives by reading the seasons correctly, a few degrees of climate change can become the difference between abundance and hunger. The question was no longer whether the Ice Age was ending. The question was why the North Atlantic climate system had turned so suddenly against the warming world. To answer that question, scientists needed something more precise than a glacier ridge, a changing shoreline, or pollen from the bottom of a lake. They needed a clock, and buried beneath Greenland, they found one. For hundreds of thousands of years, snow fell across the Greenland ice sheet. Winter snow, storm snow carrying dust from distant continents. Snow mixed with chemicals from sea spray, volcanic eruptions, forest fires, and the atmosphere itself. Each year, another thin layer settled on top of the last one. Then it got buried. The weight of new snow compressed the older layers beneath it. Soft snow became granular ice. Granular ice became solid glacier ice. Tiny pockets of ancient air were sealed inside it like messages in bottles. And because Greenland stays cold enough for this ice to survive, layer after layer accumulated into a frozen archive thousands of meters deep. Drill down through that ice, and you're not simply drilling through frozen water. You are moving backward through time. The upper layers contain relatively recent snow. Deeper down are the winters and summers of ancient civilizations. Deeper still, the last ice age. And at a particular depth, roughly 12,900 years ago, the archive records something extraordinary. A climate system changing with shocking speed. This is why Greenland ice cores became so important to the Younger Dryas story. They did not merely suggest that the climate cooled. They showed a sequence, a warming world, then a rapid reversal. Then more than 1,000 years of cold conditions. Then another abrupt shift into the warmer climate of the Holocene, the relatively stable interval in which agriculture, cities, and recorded history would eventually emerge. The ice gave scientists a timeline detailed enough to see that this was not a vague, slow wobble in climate over thousands of years. Something happened fast. How do they read it? One of the most important clues comes from oxygen. Water is made of hydrogen and oxygen, but not all oxygen atoms are identical. Most are oxygen-16, a lighter form of the element. A smaller amount is oxygen-18, which is slightly heavier. When ocean water evaporates, condenses into clouds, falls as snow, and moves through the atmosphere toward Greenland. These different forms of oxygen do not behave in exactly the same way. In colder conditions, the snow that finally reaches Greenland tends to contain less oxygen, 18 relative to oxygen 16. In warmer conditions, it tends to contain more, so when scientists measure oxygen isotopes layer by layer, they can reconstruct a powerful temperature-related signal. It is not a thermometer pushed into the ancient snow. It does not tell us that one particular day was exactly this many degrees colder. But across long sequences, especially when compared with modern observations and other climate records, it gives a remarkably detailed picture of relative warming and cooling. And at the start of the Younger Dryas, that signal drops hard. The Greenland record indicates that temperatures over Greenland fell dramatically, perhaps by around 10 degrees Celsius or more in some estimates, though the exact number depends on how the isotope signal is translated into temperature. That is Greenland, not necessarily the whole planet. Greenland was near the heart of the North Atlantic disruption, so its change was unusually intense. But the direction of the signal is unmistakable. Warmth had been building. Then the cold came back. The ice holds other clues too. Dust is one of them. During colder, windier, drier parts of the Ice Age, more dust could be lifted from exposed soils and carried across huge distances by the atmosphere. In Greenland ice cores, dusty layers often point to a harsher world, stronger winds, drier source regions, less vegetation holding soil in place, and an atmosphere moving material across continents. During the Younger Dryas, dust concentrations rose sharply compared with the warmer period just before it. Again, that does not mean every region became a desert. Climate never writes one simple story across the entire planet, but it tells us that the atmosphere around the North Atlantic had shifted into a colder, more dust-laden state. Then there are the gases. As snow becomes ice, tiny bubbles of air are trapped inside. Those bubbles preserve samples of the ancient atmosphere, carbon dioxide, methane, and other gases that people alive at the time were breathing. Methane is especially useful because much of it comes from wetlands, tropical ecosystems, biomass burning, and other biological sources. During the Younger Dryas, methane levels fell. That suggests major changes in the global systems producing it, possibly including shifts in tropical rainfall and wetlands far beyond Greenland. This is where the story becomes bigger than one icy island. Greenland tells us the North Atlantic changed abruptly. The gas bubbles suggest the disturbance was connected to changes across the broader Earth system. But even this archive has complications. The ice itself and the air trapped inside it are not exactly the same age. Snow can sit for years, decades, or longer before it compresses enough to seal off the air between its grains. So a layer of ice may be one age, while the gas bubbles inside it are somewhat younger. Scientists have to calculate that difference carefully. And the deeper you go, the more the layers become compressed and distorted by the enormous weight of ice above them. A single year near the surface may be easy to distinguish. Far below, ancient annual layers can become thin as paper, folded, stretched, or difficult to count with confidence. This is not guesswork. Researchers compare multiple cores, use volcanic horizons, chemical signals, known changes in Earth's magnetic field, and carefully modelled ice flow. But it is a reminder that even the best climate archive has uncertainty built into it. Volcanoes provide some of the most useful markers. A huge eruption can throw sulfur-rich gases high into the atmosphere. Those gases become sulfate aerosols, then eventually fall back to Earth. In Greenland, they can leave a distinctive acidic layer in the snow. If the same volcanic signal appears in separate ice cores, scientists can match those layers like matching pages from copies of the same book. These volcanic markers help lock the chronology together. They give researchers fixed points in the frozen sequence, allowing them to test annual layer counts and compare Greenland records with cores drilled in Antarctica, lake sediments, tree rings and caves. That matters enormously once we get to the more controversial parts of the Younger Dryas story, because claims about floods, extinctions, human population changes, continent-wide fires, or an impact from space all depend on timing. Did something happen before the cold began? At the beginning? Centuries later? Near the end? Those are not small details. They are the difference between a possible cause and a coincidence. The Ice Core Archive gives us the backbone of the chronology. It tells us that around 12,900 years ago, Greenland's climate shifted abruptly into Younger Dryas conditions. It tells us the cold interval lasted roughly 1,200 years. And it tells us that around 11,700 years ago, the cold ended with another sudden warming. But the ice cannot directly tell us why. It cannot point to one specific flood and prove it shut down ocean circulation. It cannot show a comet exploding overhead. It cannot identify which human communities suffered, which animals vanished, or which myths may preserve a distant memory of environmental upheaval. Ice cores record the climate response with astonishing detail. They do not automatically reveal the trigger. That distinction is where the mystery begins to sharpen. Because if the Greenland archive is right and the North Atlantic really did change this fast, then we have to ask what kind of mechanism could throw such a huge climate engine into reverse. And the answer may lie not in the sky, but in the ocean. The Atlantic Ocean is not just a giant body of water sitting between continents. It is moving. Every day, every year, every century, enormous volumes of water are flowing through it in a system so vast that no ship, no satellite image, no single measurement can show you the whole thing at once. Warm surface water moves north from the tropics. Colder water sinks in the far North Atlantic. Deep water then flows south again, eventually connecting with the other oceans of the world. Scientists call this system the Atlantic Meridional Overturning Circulation, or AMOC. That name sounds complicated. The basic idea is simpler. Think of the Atlantic as a giant conveyor belt, except it is not made of metal, and it does not move at one steady speed. It is made of water driven by wind, temperature, salt, the shape of the seafloor, and the rotation of the earth. It can speed up, it can slow down, it can shift position. Different parts of it can behave differently at the same time. But one part of this system is especially important for the climate of the North Atlantic. Warm water from lower latitudes travels northward near the surface. As it moves, it releases heat into the atmosphere. That heat helps keep northwestern Europe far warmer than it would otherwise be at the same latitude. Places like Britain, Ireland, Norway, and parts of Western Europe are much milder than comparable regions across the Atlantic in Canada. This does not mean the Gulf Stream is a magic river keeping Europe warm. That is a popular oversimplification. Winds matter. The atmosphere matters. Geography matters. But the ocean carries an enormous amount of heat northward, and that heat transfer is one of the reasons the North Atlantic climate is so sensitive. Then, as this water reaches high northern latitudes, something important happens. It gets colder. Cold water is denser than warm water. But temperature is only part of the equation. Salt matters too. When seawater contains more salt, it becomes denser. And in the far North Atlantic, especially in regions around Greenland, Iceland and the Nordic seas, water can become both cold and salty enough to sink. That sinking is one of the key processes that helps pull the larger circulation along. Imagine a bathtub with a drain at one end. Water flows toward the drain because water is leaving at the other side. In the North Atlantic, dense water sinking into the deep ocean acts a little like that drain. As surface water becomes cold and salty enough to plunge downward, more water is drawn northward behind it. Not perfectly, not instantly, not in one neat loop. But the principle is real. Warm, salty water flows north near the surface. It cools, it becomes denser. In some places it sinks. Deep water begins its long journey south, and the whole system helps redistribute heat around the planet. Now picture what happens if you add a huge amount of fresh water to the North Atlantic. Fresh water is lighter than salt water. It can sit on top of the ocean like a lid. And if enough fresh water spreads across the regions where cold, salty water normally becomes dense and sinks, it can make that surface water less salty, less dense, and less likely to plunge into the depths. The conveyor belt does not necessarily stop, but the sinking can weaken. And if the sinking weakens, the northward transport of heat can weaken too. That is the basic mechanism behind one of the leading explanations for the Younger Dryas. Not an instant global freeze, not the entire ocean switching off like someone flipped a light switch, but a major disruption in the North Atlantic's ability to move heat northward. And if you reduce the heat arriving in that part of the world, the consequences can be enormous. Sea ice can expand farther south. Snow can linger longer into spring. Colder conditions can alter storm tracks and wind patterns. A changed North Atlantic can influence rainfall over Europe, drought patterns in Africa, monsoons in Asia, and climate conditions far beyond the ocean where the disturbance began. This is why the Younger Dryas pattern matters. The strongest cooling signals appear around the North Atlantic and Greenland, exactly where you would expect a weakened overturning circulation to have its greatest effects. Europe became colder. North Atlantic sea ice expanded. Greenland experienced an especially severe return to near-glacial conditions. Other regions changed too, but not all in the same way or by the same amount. That unevenness is important. If the whole planet had simply cooled by one uniform number everywhere, we might look for one simple explanation. But climate does not work like that. The Younger Dryas was a rearrangement of the system. Some places became much colder, some became drier. Some experienced changing rainfall seasons. In the Southern Hemisphere, the timing and pattern could differ from what happened in Greenland. It was not one world wearing the same weather. It was a world with its circulation patterns disrupted. And this is where the Atlantic becomes almost frighteningly powerful. The ocean stores far more heat than the atmosphere. The upper layers of the sea can absorb, transport, and release vast quantities of energy. A shift in currents does not have to change the total amount of energy arriving from the sun. It can change where that energy goes. You can have a planet receiving nearly the same sunlight overall, while one region suddenly loses a major source of imported ocean heat. That is enough to transform landscapes. Forests can retreat. Tundra can spread. Growing seasons can collapse. Rivers can change their seasonal flow. Animal migrations can be disrupted. Human communities that had adapted to a warming post-glacial world can find themselves facing conditions their parents never knew. And the speed is the part that still captures scientists' attention. Ocean circulation is not supposed to be thought of as a simple on-off switch. The amok has multiple components. Wind-driven currents can continue even if deep water formation weakens. Water can sink in different places. Sea ice, winds, temperature and salinity all push and pull on the system at once. A freshwater pulse might affect one region strongly, while producing a more complicated response elsewhere. Climate models do not all give the same answer about exactly how much fresh water would be needed, where it would have to enter, or how long the disruption would last. Some simulations produce a dramatic slowdown. Others show a more moderate weakening. Some suggest that ice sheet changes, sea ice feedbacks, atmospheric circulation and freshwater input all had to work together. That uncertainty is not a weakness in the story. It is the story. The Younger Dryas was not caused by a cartoon version of the ocean suddenly turning off. It was likely the result of a climate system already under stress, with massive ice sheets still melting, coastlines changing, sea level rising, and huge reservoirs of fresh water trapped behind glacial barriers. The Atlantic was vulnerable because the world was in transition. The Ice Age was ending, but it was not over. And somewhere across northern North America, behind walls of ice, one of the largest lakes ever to exist was holding back a volume of fresh water almost impossible to imagine. A lake large enough that if its waters found a new path to the sea, they may have changed the balance of the Atlantic itself. Picture that lake, not a lake like Lake Superior, not even a lake like all of the Great Lakes put together. Lake Agassiz was a temporary inland sea spread across the center of North America, formed as the Laurentide ice sheet retreated, and meltwater became trapped between the shrinking ice to the north and higher ground to the south. At its greatest extent it covered an area larger than modern California. In some phases its surface stretched across parts of what are now Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. You could stand on its shore and look out across water to a horizon that seemed like an ocean. And behind that water was ice. The Laurentide ice sheet was not just a frozen landscape. It was a moving wall of ice, thousands of feet thick in places, reshaping the continent beneath it. As it melted, it released water on a scale almost beyond modern comparison. Rivers swelled, new lakes formed, old drainage routes vanished beneath ice or opened as the land rebounded. Lake Agassiz was one of the largest of these glacial lakes, and for scientists trying to explain the Younger Dryas, it has long seemed like an obvious suspect. Because that water had to go somewhere. The basic meltwater hypothesis goes like this. During the warming that followed the last glacial maximum, fresh water from Lake Agassiz and other ice-dammed lakes was draining southward through the Mississippi River system. That meant much of its water reached the Gulf of Mexico, far from the regions where North Atlantic deep water forms. But as the ice sheet shifted and retreated, the geography changed. An ice barrier could thin, a new channel could open. The land itself could rise after being released from the crushing weight of ice. And suddenly water that had been flowing one way for centuries could find a shorter route in another direction. If a major volume of fresh water was rerouted eastward or northeastward, toward the Great Lakes, the St. Lawrence Valley, the Labrador Sea, or the Arctic routes leading into the North Atlantic, it could have changed the salt balance in exactly the part of the ocean where salinity mattered most. Remember what that means. Fresh water does not need to freeze the whole Atlantic. It does not need to cover the ocean from shore to shore. It only has to interfere with the formation of dense, salty surface water in sensitive northern regions. Add enough fresh water near the wrong place at the wrong time, and surface water becomes lighter. Lighter water is less likely to sink. Less sinking can weaken overturning circulation. Less ocean heat moves north. Sea ice expands, the North Atlantic cools, and a regional disturbance begins spreading through the larger climate system. It is a terrifyingly elegant idea. A lake in North America changes its outlet. The Atlantic loses salt, and Greenland returns to Ice Age conditions. But elegance is not proof. The first challenge is timing. Scientists need more than a giant lake, and a plausible mechanism. They need to show that a drainage event happened at the right moment, that it sent enough water toward the right part of the ocean, and that the ocean responded in a way capable of producing the Younger Dryas cooling. That is harder than it sounds. Lake Agassiz did not exist in one fixed shape. It expanded and contracted. Its shorelines shifted. It merged at times with neighbouring glacial lakes, including Lake Ojibwe farther east. Its outlets changed as ice margins moved, and landscapes emerged from beneath the ice. What we call Lake Agassiz is really the history of an enormous changing water system over thousands of years, and the landscape still preserves clues. Ancient shorelines can be traced across Canada and the northern United States. Channels carved by rushing water cut through bedrock and sediment. Sands and gravels mark old spillways. River valleys that now carry modest streams are sometimes far too large for the water flowing through them today. These are the fingerprints of meltwater on a continental scale. One proposed route sent water east through the Great Lakes region and toward the St. Lawrence Valley. Another possibility involves drainage northeastward, potentially delivering fresh water closer to the Labrador Sea and the areas most relevant to North Atlantic circulation. Other routes led north or northwest toward the Arctic and the Mackenzie River system. Each route matters because where fresh water enters the ocean can matter almost as much as how much fresh water enters. Dump it into the Gulf of Mexico, and much of the water has a long, complicated journey before it reaches the North Atlantic. Send it into the Labrador Sea, and the effect could be much more immediate. Fresh water entering near regions of deep water formation has a better chance of disrupting the density-driven processes that help power the overturning circulation. Ocean models support that basic reasoning. When researchers add fresh water to sensitive areas of the North Atlantic, many simulations show a weakened circulation and cooling patterns broadly resembling parts of the Younger Dryas event. Not every model produces the same result. Not every experiment requires the same amount of water. But the mechanism is physically plausible. The geomorphology is plausible too. There were giant lakes. There were changing outlets. There were enormous floods and sustained meltwater discharges. There was a climate system already vulnerable to freshwater disturbance. The difficulty is connecting all of those pieces into one precise chain of events at around 12,900 years ago. Some reconstructions suggest that key eastern drainage routes may have opened before the Younger Dryas began. Others suggest the largest freshwater discharge may have occurred later. Dating ancient shorelines and channels is difficult. Sediments can be reworked. Ice margins do not leave clean calendar dates behind. Different dating methods can produce ranges rather than one exact year. And then there's another problem. A massive flood is dramatic. It makes for a clean story. A wall of water breaks through an ice dam, races toward the sea and changes the climate. But the real trigger may not have been one single flood. It may have been repeated pulses, seasonal discharge, a gradual rerouting that crossed a critical threshold. It may have involved Lake Agassiz, Lake Ojibwe, melting ice margins, expanding sea ice, changing winds, and feedbacks inside the ocean itself. The lake may have been the match, but the climate system was already full of dry tinder. That is why Lake Agassiz remains central to the Younger Dryas debate, without being the final answer. It gives us a credible source of freshwater on a colossal scale. It gives us physical evidence of changing drainage pathways. It gives us a mechanism that fits the North Atlantic focus of the cooling. But it does not yet give scientists universal agreement on the exact route, exact volume, exact timing, or exact sequence that pushed the climate into reversal. The mystery is not whether meltwater mattered during the end of the Ice Age. It clearly did. The mystery is whether one particular release of freshwater helped trigger one of the most abrupt climate shifts humans have ever lived through. And if it did, then the Younger Dryas may have begun not with fire from the sky, but with something quieter, a changing shoreline, a new river channel, and fresh water pouring into an ocean that was already close to breaking point. And then, after roughly 1,200 years of cold, the system shifted again. Around 11,700 years ago, the Younger Dryas ended. Not gradually. Not in the comforting way we usually imagine climates changing, a little warmer each generation, a few more trees appearing along the hillsides, winters becoming less severe over centuries. In Greenland's ice cores, the transition looks astonishingly sharp. Temperatures rose by something like 8 to 10 degrees Celsius in only a few decades, perhaps even faster in some measures. The exact pace differed from place to place. Greenland did not represent the entire planet. But the message in the ice is unmistakable. The cold regime broke. Imagine being alive in the North Atlantic world at that moment. For generations, people had adjusted to a landscape that seemed to be moving backward into the Ice Age. Forests had retreated, glaciers had stabilized or advanced in some regions. Weather patterns shifted, animal migrations changed. Places that had once been productive could become unreliable. Then the winds changed again. Warmer air returned. Sea ice retreated, growing seasons lengthened, rainfall patterns reorganized, rivers fed by melting ice swelled and changed course. Across northern Europe and North America, plants began moving north into ground that had been tundra, bare sediment, or open cold grassland for centuries. The Holocene had begun. This is the geological epoch we are still living in today. Every city, every farm, every written language, every empire, every cathedral, temple, port and highway belongs to the Holocene. It is the climatic background of everything we think of as human history. And it began with another abrupt shift. That matters because the end of the Younger Dryas was not simply the beginning event played backward. The onset of the Younger Dryas appears to have involved a complex reorganization of the North Atlantic climate system, possibly connected to fresh water, ocean circulation, sea ice and atmospheric feedbacks. The ending likely involved its own chain of events. Fresh water forcing may have weakened. Ocean circulation may have recovered. Rising greenhouse gases, changing ice sheets, and orbital conditions were all part of the larger picture. A climate system does not need to leave a cold state by reversing every step that brought it there. it can cross a threshold in a different direction. Think of a light switch that flickers. You can turn it off by pressing the switch. But it can also go dark because the bulb burns out, the power fails, or a circuit trips somewhere else in the house. The visible result is the same. The pathway is not. By the time the Younger Dryas ended, the planet had been warming overall for thousands of years. The great ice sheets were still enormous, but they were shrinking. Carbon dioxide levels were rising. Summer sunlight in the Northern Hemisphere had been changing due to slow variations in Earth's orbit. The cold interval was dramatic, but it existed inside a much larger transition out of the last ice age. Eventually, the conditions sustaining the cold state could no longer hold. And when they failed, the transformation was enormous. In Europe, birch and pine forests expanded northward. Later, denser mixed forests followed in many regions. In North America, tundra and steppe landscapes gave way, region by region, to woodland, forest, wetlands, and grasslands adapted to warmer conditions. Glaciers continued retreating, leaving behind lakes, moraines, river channels, and landscapes still visible today. Sea level kept rising too. During the Ice Age, so much water had been locked in continental ice sheets that shorelines lay far beyond their modern positions. As the world warmed, that water returned to the oceans. Coastal plains flooded, land bridges disappeared, areas that had supported hunting camps, animal herds, and human travel routes were slowly claimed by the sea. Britain became an island, the lowlands of Doggerland in the North Sea drowned. Vast stretches of the Sunda Shelf in Southeast Asia vanished beneath rising water. Around the world, people living near coasts would have watched familiar territory narrow, fragment, and disappear. Not all at once, usually not as one cinematic wall of water, but across lifetimes the change was undeniable. A hunting ground becomes a marsh becomes a bay becomes open sea. For human populations, the Holocene brought something incredibly valuable. Relative stability. That word needs a little caution. The Holocene was never perfectly stable. There were droughts, floods, cold snaps, monsoon failures, volcanic eruptions, and regional climate disruptions. Human societies still faced catastrophe. Some collapsed. Some migrated, some disappeared. But compared with the violent swings of the last glacial period, the Holocene was unusually predictable. Temperatures no longer lurched repeatedly between radically different states on the same scale. Rainfall belts still shifted, but over many regions seasonal patterns became more reliable. Forests, wetlands, and grasslands had time to establish themselves. Rivers settled into more recognizable courses. Animal populations adapted to habitats that remained in place for longer periods. And predictability changes everything. You can plant seeds only if you expect the seasons to return in something like the same order. You can invest months of labour clearing land, building storage pits, tending crops, and protecting young animals only if next year is likely to resemble this year closely enough for your effort to pay off. You can build permanent settlements only if the water source, the soil, and the local food supply are not likely to vanish after one sudden climate reversal. Agriculture did not appear the day the Younger Dryas ended. Different communities experimented with plant cultivation and animal management in different ways, over thousands of years. Some of the earliest steps toward farming may even have begun during the Younger Dryas itself, under pressure from changing environments. But the new Holocene climate created conditions in which agriculture could spread, intensify, and support larger populations. Reliable seasons made planning possible. Planning made surplus possible. Surplus made villages possible, and villages eventually became cities. That does not mean civilization was guaranteed. The Holocene offered an opportunity, not a promise. Human ingenuity, social organization, geography, plants, animals, and sheer luck all mattered. But a relatively steady climate was the stage on which farming societies could become something larger. For people who had lived through the Younger Dryas, though none of this would have felt like a geological epoch opening, it would have felt like the world changing again. The elders would remember colder years. They would remember landscapes that no longer existed. They would remember herds moving differently, rivers freezing harder, familiar plants failing to return. And now their children were growing up in a warmer world, where forests pushed across old hunting grounds and melting ice remade the map. How do people make sense of that? They tell stories. Not climate system stories, not stories about salinity, ocean overturning, orbital forcing, and ice core isotopes. They tell stories about a world that froze when it should have warmed, about waters that rose and swallowed land, about terrible winters, vanished animals, changing skies, and ancestors forced to leave everything behind. And as the climate entered its new regime, another transformation was already underway. The world of the mammoths, mastodons, giant ground sloths, and saber-toothed cats was coming to an end. The end of the Younger Dryas did not just bring warmer temperatures, rising seas, and expanding forests. It also marked the disappearance of an entire world of animals. For hundreds of thousands of years, much of the Northern Hemisphere had belonged to giants. Woolly mammoths moved across the cold grasslands of Europe, Asia, and North America in herds that may have numbered in the thousands. Mastodons browsed through North American woodlands, tearing branches from spruce and fir. Giant ground sloths, some larger than modern elephants, wandered through the Americas. There were saber-toothed cats, short-faced bears, ancient horses, camels, giant beavers, musk oxen, giant bison, and predators built to hunt prey far larger than anything alive today. Then, in geological terms, they were gone. By the beginning of the Holocene, most of the largest animals in North America had disappeared. Mammoths vanished from the mainland. Mastodons vanished. Horses that had evolved in North America vanished, only to be reintroduced thousands of years later by Europeans. Camels vanished. Giant ground sloths vanished. Saber-toothed cats vanished. The American lion vanished. The short-faced bear vanished. South America lost its own spectacular giants. Giant sloths, armoured glyptodonts that looked like car-sized armadillos, elephant-like gomphothers, and massive native hoofed animals found nowhere else on Earth. Europe and Northern Asia were hit too, though not in exactly the same way or at exactly the same time. Woolly rhinoceroses disappeared. Cave lions disappeared. Cave bears had already been declining. Many cold-adapted animals either retreated north, shrank into isolated populations, or vanished completely as the Ice Age world dissolved around them. It is tempting to tell this as one clean story: the climate changed. The animals died, or humans arrived. The animals died, or something fell from the sky. The animals died. But the real story is harder than that, and much more interesting, because there was no single extinction date. Different species disappeared at different times. Different regions lost animals on different schedules. Some populations were already declining before the Younger Dryas began. Others survived well into the warming that followed it. And a few famous species held on in isolated refuges for thousands of years after their mainland relatives were gone. Woolly mammoths are the clearest example. On the mainland, mammoths disappeared from most of their range near the end of the last ice age. But isolated mammoth populations survived on islands long afterward. On St. Paul Island in Alaska, they persisted until roughly 5,600 years ago. On Wrangel Island in the Arctic Ocean, a small population survived until around 4,000 years ago. That is later than the pyramids of Egypt, so the extinction was not one instant. It was a process, a long collapse that may have happened quickly in some places, slowly in others, and differently for every species. Still, the timing is impossible to ignore. In North America especially, many large animal extinctions cluster around the Pleistocene-Holocene boundary, broadly between about 13,000 and 11,500 years ago. That overlaps with the Younger Dryas and the dramatic environmental upheaval surrounding it. And that overlap is why the extinctions became central to arguments about catastrophe. The first suspect is climate. The world these animals had adapted to was disappearing. Mammoths were not simply animals of snow and ice. They thrived in what scientists call the mammoth steppe, a vast, cold, dry, grassy ecosystem stretching across northern Eurasia and North America. It was not modern tundra. It was a productive landscape of grasses, herbs, sedges, and open ground, capable of supporting enormous herds. As the climate warmed, that ecosystem fragmented. In some places, wetter conditions encouraged forests, peatlands and shrubs. In others, melting ice transformed drainage patterns. Seasonal cycles changed. Snow became deeper or wetter. Plant communities shifted faster than large animals could adapt. A mammoth built for open grassland cannot simply move into dense woodland and carry on as before. For mastodons, the problem may have been different. They were more closely tied to forests and wetlands, but changing vegetation, unstable water systems, and disease pressures may have affected them in ways we still do not fully understand. Then there were humans. By the late Ice Age, people had spread across much of the world. In the Americas, humans were present by at least the terminal Pleistocene, although the exact timing and routes of migration remain intensely debated. They were skilled hunters. They had stone-tipped weapons, social coordination, knowledge of animal behavior, and growing populations moving into landscapes full of prey that had never encountered humans before. Even limited hunting pressure can be devastating if an animal reproduces slowly. Elephants are the obvious modern comparison. They mature late. They have long pregnancies. They produce relatively few young. Kill adults faster than the population can replace them, especially breeding females, and the decline can become irreversible. Mammoths and mastodons likely faced the same vulnerability. But hunting alone does not solve the puzzle either. There are archaeological sites showing humans hunted mammoths, mastodons, and other large animals. That much is clear, but direct evidence of hunting exists for only a fraction of extinct species. And humans had lived alongside megafauna in Africa and Eurasia for tens of thousands of years, without wiping out every large animal they encountered. So perhaps the question is not climate or humans. Perhaps it is climate plus humans. A population already stressed by changing habitat, disrupted migration routes, shrinking food supplies, and unstable seasons becomes far more vulnerable to even modest hunting. Add drought, harsh winters, flooding, wildfire, competition, or disease, and a species may cross a point from which it cannot recover. Disease has been proposed as well. Humans, dogs, or other migrating animals could theoretically have introduced pathogens into populations with little resistance. It is a plausible mechanism in principle, but unlike climate change or hunting, direct evidence for a continent-wide disease event at the end of the Ice Age remains thin. The frustrating answer is also the most honest one. There may not have been one cause. The extinction crisis was probably a cascade. Climate transformed habitats. Habitats altered food supplies. Small populations became isolated. Humans added pressure. Some species endured, others did not. And once numbers fell low enough, bad luck itself became lethal. One failed breeding season, one severe drought, one disease outbreak, one local flood, and a surviving population could disappear forever. But catastrophe arguments focus on the timing because the losses look so dramatic. If mammoths, mastodons, sloths, horses, camels, and predators all vanished in a narrow window, then maybe something sudden happened. Maybe there was a rapid climate shock beyond anything ordinary. Maybe widespread fires swept the continents. Maybe an impact event struck Earth and triggered collapse. Those ideas would become enormously controversial. But before the argument turns to fire from the sky, there is another mystery waiting in the archaeological record. At almost the same moment, the great animals were disappearing. One of North America's most famous ancient cultures was changing too. That culture was Clovis. For much of the 20th century, Clovis stood at the centre of the story of the first Americans. Clovis sites were found across an astonishing area of North America, from the Great Plains to the southwest, from the eastern woodlands to the Rocky Mountains. Their signature was a distinctive stone spear point, long, carefully shaped, fluted down the centre, and designed to be fitted into a wooden shaft. These were not crude tools. Making a Clovis point required planning, skill, and nerves. A craftsperson had to select the right stone, shape it through a sequence of precise strikes, thin it without snapping it, then remove a long flake from the base to create the flute. One mistake could ruin hours of work. Yet Clovis points appear across thousands of miles, often made from stone, carried far from its geological source. That tells us something important. The people who made them were mobile. They knew the landscape. They moved through long-distance social networks. They shared techniques across enormous territories. And they were living in a North America that was changing beneath their feet. For decades, archaeologists believed Clovis people were the first humans in the Americas. The model was simple. During the last ice age, people crossed from Siberia into Alaska across Beringia, the land bridge exposed when sea levels were lower. Then, when ice sheets began retreating, they moved south through an ice-free corridor in western Canada. Clovis technology appeared. The continent was settled. End of story. It was neat, it was elegant, and it was wrong, or at least incomplete. The problem was that evidence began appearing at sites older than Clovis. At Monte Verde in southern Chile, archaeologists found evidence of people living there more than 14,000 years ago, before Clovis technology appeared in North America. Other sites, including Paisley Caves in Oregon, the Buttermilk Creek Complex in Texas, Cooper's Ferry in Idaho, and several others, have added to the case that humans were already present in the Americas before the classic Clovis period. Not every proposed pre-Clovis site is accepted. Some dates are disputed. Some artifacts may be natural fractures rather than human tools. Archaeology is full of arguments because the evidence is often fragmentary, buried, disturbed, and incredibly old. But the wider conclusion is now hard to avoid. Clovis was not the beginning. It was one major cultural tradition within a deeper and more complicated human history in the Americas, and that matters for the Younger Dryas story. Because if Clovis people were the first Americans arriving suddenly and spreading rapidly, just as the megafauna disappeared, then the narrative almost writes itself. New hunters enter a continent full of vulnerable animals. Extinctions follow. Perhaps climate change makes it worse. Perhaps catastrophe accelerates everything, but once people are known to have been in the Americas earlier, the timeline becomes less tidy. Humans had already been adapting to American landscapes before the Younger Dryas began. They had already found coastlines, river valleys, uplands, forests, and grasslands. They had already developed local knowledge. They may have arrived by multiple routes, including coastal routes, now drowned beneath rising seas. So the question changes. Not, did humans suddenly appear at the moment of collapse? But how did already established human populations respond when the world became colder, drier, wetter, more unstable, and ecologically unfamiliar? That is where the archaeological transition gets interesting. Clovis technology appears near the beginning of the Younger Dryas, roughly 13,000 years ago depending on how the dates are calibrated. Then, within a relatively short span of time, classic Clovis points largely disappear from the record. In many regions they are followed by different point styles and different hunting strategies. On the Great Plains, for example, the Folsom tradition emerges. Folsom points were smaller, more finely fluted, and strongly associated with bison hunting. This was not just a change in decoration, it may reflect a changing world. Clovis hunters lived alongside mammoths, mastodons, ancient horses, camels, giant bison, and other animals that were disappearing or becoming rare. Folsom hunters lived in a landscape where many of those giants were gone. Bison became more important. Hunting became more specialized in some places. Toolkits changed because the prey changed. Imagine what that would mean at the level of an individual community. For generations, people may have known where mammoths moved in spring. They may have known the river crossings, the seasonal grazing grounds, the places where a herd could be trapped against a bluff or a muddy bank. Their tools, stories, travel routes, and social relationships may all have been shaped by those animals. Then the herds thin out. A familiar hunting ground produces nothing. A route passed down by grandparents no longer works. The animals that once fed a large group are replaced by smaller, faster, more scattered prey. Suddenly the old knowledge is not useless, but it is no longer enough. That kind of change can be devastating. But devastating is not the same as total collapse. This is one of the places where catastrophe narratives can outrun the evidence. The disappearance of Clovis points does not prove that Clovis people vanished in a single disaster. Archaeological cultures are not biological species. A point style can disappear because people changed their technology, shifted territories, altered their social networks, or adapted to new prey. The descendants of Clovis communities may well have become Folsom peoples, Western-stemmed peoples, or other regional populations whose identities we can only partly see through stone. A tool tradition ending is not necessarily a population ending, and the archaeological record itself is selective. Organic tools usually rot. Campsites are buried, eroded, flooded, or destroyed. Rising seas swallowed huge areas of ancient coastal landscape, possibly including some of the earliest American settlements. What survives is not the whole past, it is the small, hard, durable fraction of the past that chance allowed us to find. Still, the transition is real. Near the Younger Dryas boundary, North America saw ecological disruption, megafaunal decline, changing tool traditions and shifts in how people used the land. That combination deserves attention. It suggests that human societies were adapting under serious pressure. But archaeology gives us a more complicated picture than a continent-wide apocalypse. There is no clear evidence that every community was wiped out at once. No universal burn layer, no single horizon of abandoned settlements stretching from Alaska to Patagonia. No unmistakable sign that an advanced civilization vanished overnight. What we see instead is variation. Some groups may have suffered terribly. Some may have moved, some may have merged with neighbouring communities. Some may have changed what they hunted, where they travelled, and how they made tools. Some may have survived precisely because they were flexible enough to abandon old strategies before those strategies became fatal. And that flexibility may be the real lesson of the Clovis transition. The end of the Ice Age did not produce one human response. It produced thousands of local responses shaped by rivers, animals, weather, kinship, knowledge, and luck. But for some researchers, that is still not enough to explain the strange clustering of changes near 12,900 years ago. They argue that the world did not merely shift. They argue that something struck it. That idea is known as the Younger Dryas impact hypothesis. In its broadest form, the hypothesis proposes that around 12,900 years ago, Earth encountered fragments from a comet or asteroid, not necessarily one giant object hitting one obvious place. The proposed event may have involved multiple fragments breaking apart in the atmosphere, exploding as airbursts, or striking different parts of the planet nearly simultaneously. And if that sounds dramatic, it is. The hypothesis was never just an attempt to explain a strange layer of sediment. It was an attempt to connect several mysteries that appear close together in time. The abrupt onset of Younger Dryas cooling, major ecological disruption. The disappearance of many large animals in North America. Evidence for widespread burning. And the transition away from Clovis technology. For supporters, these events do not look like separate chapters. They look like consequences. Picture the world 12,900 years ago. Ice sheets are retreating, forests and grasslands are shifting north. Sea levels are rising. Human communities are spread across North America, hunting, gathering, trading, adapting to landscapes their grandparents might barely recognize. Then something enters the atmosphere at cosmic speed. A comet fragment does not need to reach the ground intact to cause devastation. If it breaks apart high in the atmosphere, the energy release can be enormous. The shock wave can flatten forests. Heat can ignite fires. Material blasted upward can rain back over vast areas. Depending on the size, angle, composition, and location of the object, the effects could be regional or even global. This is what researchers mean by an airburst. The best-known modern comparison is the Tunguska event in Siberia in 1908. An object, probably a small asteroid or comet fragment, exploded in the atmosphere and flattened an immense area of forest. No confirmed crater was left behind, but the destruction on the ground was unmistakable. Supporters of the Younger Dryas impact hypothesis suggest something much larger and more complex may have happened at the end of the Ice Age. Not one Tunguska, potentially many. Perhaps a fragmented comet entered Earth's atmosphere and scattered debris across the Northern Hemisphere. Some fragments may have exploded in the air, some may have hit ice sheets, leaving little or no lasting crater because impacts into thick ice are difficult to detect thousands of years later. Others may have struck the ocean, others may have produced smaller, more conventional impacts on land. That distinction matters. A conventional impact is what most people imagine. A solid asteroid or comet strikes the ground, excavates a crater, throws rock and dust into the atmosphere, and leaves behind a scar that can survive for millions of years. An airburst is different. The object explodes before it reaches the surface. It can still be destructive, but it may leave no crater at all. And then there is the multiple impact scenario. This is the version most often associated with the Younger Dryas hypothesis. Not a single clean impact site, but a debris field of cosmic fragments arriving over a short period of time, perhaps minutes or hours, perhaps across a much wider area. It is a theory built for a mystery with no obvious smoking gun. Because despite decades of searching, no universally accepted crater has been identified as the place where the Younger Dryas catastrophe happened. That has not stopped the hypothesis from attracting enormous attention. Partly because it offers a simple, powerful answer to a complicated moment in prehistory. Climate systems are difficult. Ocean circulation is difficult. Ice sheet collapse, meltwater pulses, ecosystem shifts, human hunting pressure, disease, and regional drought are difficult. A cosmic impact feels like a single match dropped into a world already soaked in gasoline. It also captures the imagination because Earth has been hit before. Around 66 million years ago, an asteroid struck near what is now Mexico and helped end the age of non-avian dinosaurs. Impact events are not fantasy. They are part of planetary history. The question is not whether objects from space can transform life on Earth. They can. The question is whether one did so at the beginning of the Younger Dryas. And that question comes down to a thin, dark, scattered layer in the ground. At dozens of sites across North America, and later at sites in other parts of the world, researchers reported unusual material at roughly the same point in time. Near the beginning of the Younger Dryas, about 12,900 years ago. This proposed layer is often called the Younger Dryas boundary. In some locations it appears as a dark band of sediment. In others it is identified through microscopic particles, chemical signatures, burned material, or unusual concentrations of certain elements. The layer is not identical everywhere. It is not always easy to date, and it is not preserved at every site. But for supporters, it is the core of the case. They argue that this boundary contains traces of extraordinary heat, extraterrestrial material, and widespread environmental disturbance, tiny objects that may have formed in high-temperature events, carbon-rich layers that may record major fires, minerals and metals that may point toward cosmic debris. In later sections we will look closely at those claims, because each one has become a battlefield of scientific argument. And this is where we need to be careful. The Younger Dryas impact hypothesis is not the accepted explanation for the Younger Dryas. The leading explanation remains tied to climate processes, especially the disruption of Atlantic Ocean circulation by massive pulses of fresh water from melting ice sheets and glacial lakes. But leading does not mean every detail is settled. Scientists still debate exactly how the climate reversal began, how quickly it spread through different regions, how it affected ecosystems, and how its timing relates to extinctions and cultural changes. Into those gaps the impact hypothesis entered with a bold alternative. Maybe the climate system was already vulnerable. Maybe melting ice and shifting oceans had loaded the mechanism. But maybe something from space pulled the trigger. And if you want to go deeper into mysteries where the evidence is real, the questions are huge, and the answers remain unsettled, you can get the channel's book about the 12 unexplained mysteries on our website. The link is in the description, because the strange thing about this hypothesis is not that it asks whether disaster came from the sky. Humans have always asked that question. The strange thing is that researchers believe they may have found a physical trace of that disaster, buried in soil, lake beds, and ancient archaeological sites, waiting beneath nearly 13,000 years of history. But finding an unusual layer is not the same as proving a cosmic impact. To understand why some scientists see evidence of a shattered comet, while others see ordinary Earth processes being forced into an extraordinary story, we need to examine what, exactly, they say the boundary contains. Start with platinum. Platinum is rare in Earth's crust. It is not impossible to find in ordinary sediments, but it is unusual enough that a sharp spike in platinum concentration gets attention, especially when that spike appears close to a proposed catastrophe layer. At a number of sites associated with the Younger Dryas boundary, researchers have reported elevated platinum concentrations. Some of the best-known reports come from North America, including archaeological and sedimentary sites where the proposed boundary falls near 12,900 years ago. Other studies have described possible platinum anomalies in Greenland ice cores and in sites farther from North America. For supporters, this matters because platinum belongs to a family of elements often associated with meteorites and cosmic dust. The famous dinosaur-killing impact boundary, 66 million years ago, contains an iridium anomaly. Iridium is exceptionally rare in the crust, but relatively more common in certain extraterrestrial materials. The Younger Dryas case is not a simple repeat of that discovery. The reported signal is usually platinum, not a globally uniform iridium layer. But the basic logic is similar. If material from a comet or asteroid entered the atmosphere, exploded or struck the surface, tiny amounts of extraterrestrial debris could become mixed into sediments. Thousands of years later, a chemical analysis might reveal an unexpected platinum peak, exactly where the event is supposed to have happened. That is the interpretation. The observation is narrower. In some samples, researchers have measured more platinum than in layers above or below. Those are not the same statement. A platinum spike does not arrive with a label saying, "I came from a comet." Platinum can be concentrated by terrestrial processes. Sediments can be disturbed. Different laboratories can produce different results depending on how samples are collected, prepared, and measured. And perhaps most importantly, a spike only becomes powerful evidence if it can be reproduced at many sites, dated reliably, and shown to occur in the same narrow window of time. Then there are the tiny beads. Microspherules are microscopic rounded particles, often made of glassy or metallic material. They can form when molten droplets cool while flying through the air. An impact can make them. A powerful airburst may make them, but so can volcanic eruptions, industrial contamination, wildfires under certain conditions, and other high-temperature processes. Supporters of the impact hypothesis have reported unusual microspherules in Younger Dryas boundary sediments. Some are rich in iron, some contain titanium or other minerals, and some have textures that researchers argue are consistent with rapid heating and cooling at extreme temperatures. The argument is not simply that these spheres exist. Microspherules exist in many environments. The argument is that certain types appear in unusual abundance at the proposed boundary across a wide geographic area. If thousands of sites showed the same distinctive particles, all appearing in deposits laid down at almost exactly the same time, that would be difficult to dismiss as a local wildfire or a single volcanic eruption. It would suggest a shared event, or at least a shared process. Another contested category is melt glass. This is glass formed when mineral-rich material is heated enough to melt, and then cool rapidly. On impact sites, melt glass can be a major clue. The energy released by a large impact is more than enough to melt rock, soil, and ice-associated debris. Supporters have described glassy material from several boundary sites that they say formed under temperatures too high for ordinary fires. Some of these materials have been compared to glass associated with known impact events or nuclear test sites. The claim is dramatic, that the boundary contains material exposed to temperatures reaching well beyond what a burning forest could normally produce. But again, the crucial question is not whether the glass is real. The question is what made it. Glass chemistry can be altered after burial. Natural fires can create vitrified material. Volcanoes make glass constantly. Lightning can fuse sand into glassy tubes called fulgurites. And determining formation temperature from a tiny, weathered particle is not always straightforward. One research group may see an impact signature, another may see material produced by local burning, sedimentary reworking, or contamination. Then come nanodiamonds. Diamonds are usually imagined as large crystals locked deep in the earth. Nanodiamonds are different. They are particles so small that millions could fit across the width of a human hair. Some forms can be produced by intense shock pressures, including impacts. That is why reports of nanodiamonds in Younger Dryas boundary layers became one of the hypothesis's most attention-grabbing claims. A cosmic collision can generate immense pressure. So can an atmospheric explosion under certain extreme conditions. If nanodiamonds were widespread, confined to a narrowly dated boundary, and found alongside other unmistakable impact markers, they would strengthen the case considerably. But nanodiamonds are difficult to identify with certainty. They can occur in meteorites, but they can also be formed through terrestrial processes. Different laboratories have challenged whether some reported particles were correctly classified, whether they were truly impact-related, and whether they appeared consistently enough to support a single event. This is a recurring pattern in the Younger Dryas debate. The individual observations may be interesting. The interpretation is the fight. The boundary layer has also been reported to contain soot, charcoal, and carbon-rich material. At first glance, this seems easier to understand. Soot and charcoal mean burning. A great deal of it could indicate widespread fires. And widespread fires fit naturally into a scenario where airbursts sent thermal radiation across forests and grasslands, igniting vegetation over huge areas. But the end of the Ice Age was already a world in transition. Forests were spreading into newly ice-free territory. Vegetation zones were shifting. Dry periods occurred in some regions. Humans used fire. Natural lightning fires happened. Charcoal records can rise and fall for reasons that have nothing to do with objects from space. A dark, carbon-rich layer can tell us that burning occurred. It cannot, by itself, tell us why. For the impact hypothesis to become compelling, all these clues would need to line up. Platinum peaks, microspherules, high-temperature glass, possible nanodiamonds, soot and charcoal. They would need to appear across continents in undisturbed deposits, all precisely tied to the start of the Younger Dryas. Not roughly around then, not somewhere in the same millennium, at the same boundary, because a single extraordinary event should leave a synchronized fingerprint. A wildfire in one valley, a flood in another, and a volcanic eruption centuries later can create strange sediments. But a cosmic debris swarm crossing the Northern Hemisphere should create markers that appear nearly simultaneously over a very wide area. That is the standard the hypothesis has to meet. And then there are the Carolina Bays. These are thousands of shallow oval depressions scattered across the Atlantic coastal plain of the United States. Many are aligned in similar directions. From the air they can look almost unnervingly deliberate, like someone pressed a field of giant fingerprints into the landscape. Some impact hypothesis supporters have suggested they were formed or reshaped by ejecta, falling from a major impact, perhaps on or near the Laurentide ice sheet. In that scenario, material blasted into the atmosphere rained down across the southeast, striking the ground at high speed and carving the bays. It is an intriguing image, but it is not the geological consensus. Most geologists explain the Carolina Bays through combinations of wind, water, sediment movement, lake processes, and changing climate over long periods. Many bays appear to have complex histories, with sediments and dates that do not fit a single sudden formation event 12,900 years ago. Their orientation may reflect prevailing winds rather than incoming debris from the sky. The bays are real, their strange geometry is real. The claim that they are impact scars remains disputed, and that distinction is the whole story in miniature. The Younger Dryas boundary contains observations worth investigating. Unusual chemical concentrations, tiny particles, burned material. Odd landscape features, none need to be invented. But evidence is not just a list of strange things. Evidence is a chain. Each link has to hold, the samples must be correctly identified, the layers must be securely dated, the patterns must be reproducible, and alternative explanations must be tested seriously. Because if even one link breaks, a cosmic catastrophe becomes less certain. Not impossible, just unproven. That is why many scientists remain unconvinced, not because they think the Younger Dryas never happened. The Younger Dryas is real. The abrupt cooling is recorded in Greenland ice cores, lake sediments, pollen records, cave deposits, ocean sediments, and glacial evidence across much of the Northern Hemisphere. Around 12,900 years ago, climate conditions changed dramatically. Then, about 1,200 years later, the world shifted again into the warmer Holocene. That part is not the controversy. The controversy is what triggered it. Was this a climate system already destabilized by melting ice sheets and changing ocean circulation? Or did a cosmic impact, or a series of air bursts, deliver the shock that pushed the system over the edge? Those are very different claims, and the second claim requires very strong evidence. Start with reproducibility. In science, one laboratory finding something unusual is interesting. Two laboratories finding it independently is more interesting. But for a claim this large, researchers need to be able to collect new samples, use clear methods, and find the same signal again and again. This has been difficult. Some studies have reported platinum anomalies at the Younger Dryas boundary. Others have not found them, or have found peaks at different depths, different dates, or in layers that may have been disturbed after deposition. The same pattern appears with microspherules, melt glass, and nanodiamonds. One team reports a distinctive concentration. Another team samples a nearby site, or even the same site, and finds a weaker signal, no signal, or particles that do not match the original description. That does not automatically mean anyone is wrong. Ancient sediments are messy. A layer buried for nearly 13,000 years can be churned by roots, insects, groundwater, burrowing animals, freeze-thaw cycles, erosion, flooding, and human excavation. In some places, material from different periods gets mixed together. A particle deposited centuries before the Younger Dryas might be moved downward. A younger particle might work its way into an older layer. What looks like one sharp moment in time can become blurred into a band of sediment, several centimetres thick, and several centimetres can represent decades, centuries, or more. That creates a serious problem for an impact hypothesis. The proposed event is supposed to have been sudden, maybe minutes, maybe hours. At most, a brief episode compared with the scale of geological time. Its debris should form a narrow, well-dated horizon. If the markers appear across a broad range of depths and ages, the case becomes harder to make. Then there is contamination. Modern industrial activity produces tiny metal-rich particles, fly ash, glassy spheres, and combustion residues. Laboratories themselves use materials that can introduce trace contaminants if procedures are not extremely careful. Even excavation tools, storage containers, adhesives, and handling can affect a sample. No one is suggesting that every disputed result is contaminated, but when the evidence consists of microscopic particles and small chemical anomalies, contamination has to be ruled out, not merely assumed away. A few grains of modern material can look very important if the original sample is tiny. Sample selection matters too. Imagine searching dozens of locations, measuring hundreds of sediment layers, and focusing attention on the sites that contain the most unusual results. You may find real anomalies, but if the less dramatic sites are never published, or are treated as unimportant, the overall pattern can look stronger than it really is. This is not fraud. It is a basic danger in any search for rare signals. The more extraordinary the pattern being proposed, the more important it becomes to report the misses as well as the hits. There is also a simpler issue. Many of the proposed markers do not belong exclusively to impacts. Platinum can arrive in cosmic dust, but it can also be concentrated by ordinary geological processes. Microspherules can form in impacts, but also in volcanoes, fires, industry, and other high-temperature environments. Charcoal can record massive burning, but fires do not need a comet to start. Nanodiamonds may indicate extreme conditions, but identifying their exact form and origin is technically difficult. Melt glass may form at extraordinary temperatures, yet natural processes can create glassy materials too. So scientists ask a relentless question. What explanation accounts for the evidence with the fewest assumptions? If a charcoal peak can be explained by changing vegetation, drought, lightning, and human fire use, then charcoal alone cannot prove a cosmic disaster. If a platinum anomaly appears at only some sites, then it may be important, but it is not yet a global fingerprint. If unusual particles can form in several ways, researchers need independent evidence showing which process actually made them, and that brings us to the missing crater. A major impact capable of causing continent-scale destruction should, in many scenarios, leave an obvious scar. A crater shocked minerals, a large ejecta blanket. A geological wound that can be mapped, dated and studied. So far, there is no universally accepted crater of the right age and scale. Supporters have proposed several possibilities. Some suggest an object exploded in the atmosphere, which might leave little or no crater. Others propose impacts into the Laurentide ice sheet, where thick ice and later glacial erosion could conceal or destroy much of the evidence. There are even proposals for structures beneath ice, beneath lakes, or offshore. These are possibilities, but possibilities are not discoveries. A hidden crater can explain why no crater is visible. It cannot substitute for finding one, until researchers identify a structure with clear impact features and a secure date near the start of the Younger Dryas. The hypothesis remains incomplete. That is how scientific debate is supposed to work. A bold idea appears. It explains some strange observations. Other scientists test the samples, challenge the methods, look for alternative explanations, and search for predictions the idea should make. Sometimes the evidence grows stronger. Sometimes a claim fades. Sometimes the original idea survives, but in a smaller and more precise form than its first supporters imagined. The Younger Dryas impact hypothesis is still in that process. It has not been proven. It has not been completely ruled out. But the broad scientific view remains cautious. The climate reversal itself is firmly established, while a cosmic catastrophe at its beginning remains unconfirmed. And that caution matters, because the end of the Ice Age was already a world capable of producing enormous upheaval without anything falling from the sky. And one of the biggest claims is written in black. Charcoal, at sites across North America, and at some locations beyond it, researchers have reported dark layers near the beginning of the Younger Dryas. Sediments containing charcoal, soot-like carbon, burned plant material, and particles that may reflect intense heat. To supporters of the impact hypothesis, these layers suggest something almost unimaginable. A continent-scale fire event, forests and grasslands igniting across enormous distances, smoke darkening the sky, animals trapped between flames, freezing temperatures and collapsing food supplies. Human communities watching familiar landscapes turn into ash. It is a powerful picture, and parts of it may contain something real. The end of the last ice age was not environmentally peaceful. Ice sheets were retreating, sea levels were rising, rivers were changing course, vegetation zones were moving northward, sometimes over surprisingly short periods of time. A place that had once been open grassland could become shrubland. A woodland could become tundra. Wet areas could dry out. Dry areas could flood. In a world like that, fire regimes could change dramatically. But a charcoal layer does not come with a label explaining what caused it. It tells us that vegetation burned. Sometimes it tells us a great deal burned. But it does not automatically tell us whether the fire was local, regional, continental, or global. It does not tell us whether it was started by lightning, drought, human activity, volcanic processes, or fragments from space. This is where the scale of the record matters. Imagine a lake at the edge of an ancient forest. Every year pollen blows onto its surface, dust settles, ash drifts in. Floods carry soil from the surrounding hills. The lake bottom slowly builds a layered archive of the landscape around it. If a major fire burns nearby, charcoal enters the sediment. A sharp charcoal peak may appear in the record. That is valuable evidence. But it is still evidence from one lake, in one drainage basin, receiving material from one particular region. A fire 50 miles away might leave a weak signal. A fire right beside the lake might leave a huge one. Wind direction matters, rainfall matters, the type of vegetation matters. A grass fire can burn fast and leave a different charcoal signature than a forest fire. A series of smaller fires over decades can sometimes produce a layer that looks, at low resolution, like one dramatic episode. So when scientists compare charcoal records, they ask difficult questions. Are the layers securely dated? Do they occur at exactly the same time? Are they found across many environments or only a handful? Do they represent a sudden spike in burning or a longer period of changing fire activity? And do the charcoal particles indicate nearby flames, distant smoke, or material washed in long after the fire was over? The answer so far is complicated. There is evidence for substantial biomass burning in some regions around the Younger Dryas boundary. There are charcoal peaks, there are black carbon measurements. There are sediments that suggest disturbed soils, changing vegetation, and unusual environmental stress. But the evidence does not yet show that all of North America, much less the entire planet, erupted in one synchronized firestorm. That distinction is not a minor technical detail. It is the difference between a world experiencing severe regional ecological disruption and a world-ending inferno caused by a cosmic strike. Dust tells a similar story. Some paleorecords show changes in dust deposition around this period. That makes sense. When climates become colder, drier, windier, or less stable, landscapes can lose protective vegetation. Exposed soils become vulnerable. Rivers can carry more sediment. Glaciers grind rock into fine particles. Strong winds lift dust into the atmosphere and carry it across continents and oceans. Dust can be a sign of environmental disturbance, but it is not a fingerprint of a single cause. A drying grassland produces dust. A collapsing ice sheet produces dust. Expanding deserts produce dust. Floods, followed by drought, produce dust. Even the movement of large herds across damaged ground can contribute to erosion. At the beginning of the Younger Dryas, several of these processes may have been happening at once. That is what makes this period so difficult to reduce to one dramatic event. The climate system was already in motion. The ice sheets were melting. Ocean circulation may have been changing. Vegetation was shifting. Animals were responding to a landscape that could transform within a few human generations. Then the Younger Dryas brought renewed cold, altered rainfall, and growing seasonal instability across much of the Northern Hemisphere. For large animals, that could be devastating even without fire from the sky. A mammoth does not need to be struck by an airburst to suffer. If the plants it depends on disappear, if water sources shift, if winters become harsher, if migration routes are blocked by new wetlands or expanding ice, survival becomes harder. The same is true for horses, camels, mastodons, giant ground sloths, and the predators that hunted them. And humans were not outside that crisis. Small hunter-gatherer groups depended on intimate knowledge of landscapes. They knew where animals moved, where seasonal plants appeared, where rivers could be crossed, where stone could be found, where shelter was reliable. But what happens when the river changes, when the herd never arrives? When a familiar valley becomes too cold, too dry, too wet, or too dangerous to use, you move, you adapt, or you disappear. That does not mean climate alone caused every extinction, or that fire alone destroyed every ecosystem, or that humans played no role. Human hunting pressure may have mattered in some places. Habitat change clearly mattered. disease has been proposed. So have complex combinations of these forces different in different regions. The evidence supports environmental upheaval. It supports changing fire patterns. It supports dustier, more unstable landscapes in some records. It supports real stress on ecosystems and human communities. What it does not yet support is a proven single-day collapse of the entire living world. Maybe some regions experienced sudden destruction. Maybe fires did flare across vulnerable landscapes as climate shifted. Maybe an external event added to the chaos. But the broad picture may be more unsettling than one clean apocalypse. Not one blow, a cascade. A world changing fast enough that the old rules of survival stopped working. And if a world can change through a cascade rather than one single blow, then people living through that change would have needed more than luck to survive. They would have needed memory of where water could still be found, memory of which animals had vanished and which plants still grew after a bad season, memory of old roots, old dangers, old stories, and perhaps in some places they began turning that memory into something more permanent. Stone in southeastern Turkey, on a hill called Göbekli Tepe, archaeologists uncovered one of the most extraordinary sites from the beginning of the Holocene. Its oldest known monumental enclosures date to roughly 11,600 years ago, almost exactly at the transition out of the Younger Dryas. That timing is why the site has become so important. Göbekli Tepe was built in a world coming out of climate instability. The cold phase was ending. Rainfall patterns were shifting. Wild cereals and animal populations were becoming more reliable in parts of Southwest Asia. Human groups were beginning to settle more intensively in productive landscapes, though agriculture, at least in its fully developed form, had not yet arrived. And there, on a limestone ridge, people built enormous circular and oval enclosures. At the centre of these structures stood massive T-shaped limestone pillars, some more than 16 feet tall and weighing many tons. Around them were smaller pillars set into stone walls. Many were carved with animals: foxes, snakes, boars, wild cattle, cranes, scorpions, spiders, and birds with outstretched wings. Some pillars appear almost human. They have arms carved along their sides, hands meeting at the front, belts around their waists, and cloth-like details descending toward the ground. They may represent ancestors, spirits, gods, powerful individuals, or beings whose meaning has been lost completely. Whatever they were not casual decorations. Göbekli Tepe tells us that people who were still largely hunter-gatherers could organize labor on an astonishing scale. They could quarry stone, shape it, move it, coordinate large gatherings, feed workers, maintain shared rituals, and create monuments that seem designed to bring many groups together around a common identity. That fact alone is revolutionary. For a long time, the standard story went like this: first agriculture, then permanent villages, then food surpluses, then temples, then complex religion. Göbekli Tepe complicated that sequence. It suggested that communal ritual and large-scale cooperation may have helped drive people toward more settled ways of life, rather than simply appearing after farming had already transformed society. But Göbekli Tepe has also attracted a more dramatic interpretation. Some writers believe its carvings preserve a memory of the Younger Dryas catastrophe itself. Not just a general memory of hardship, but a specific account of a celestial event, a comet or fragmented object striking Earth, igniting fires, causing darkness, and triggering the sudden return to Ice Age conditions. The centerpiece of this argument is a relief known as Pillar 43, often called the Vulture Stone. It shows a dense and strange collection of images. A large bird, possibly a vulture, spreads its wings. Below and beside it are other animals, including a scorpion. There are abstract shapes, a headless human-like figure, and a series of symbols that some researchers have interpreted as a coded astronomical message. The proposed reading goes something like this. The animals represent constellations. The scorpion represents Scorpio. Other figures correspond to regions of the ancient sky. A circular symbol may represent the sun. And the entire arrangement records the position of the stars at the time of a devastating comet impact, around 10,900 BCE, near the beginning of the Younger Dryas. It is an extraordinary idea. Imagine it. A monument built thousands of years before writing, preserving a warning from the sky. A message carried through generations by people who had watched the world burn, darken, freeze, and change beyond recognition. The problem is that this interpretation requires a long chain of assumptions. First, we would need to know that the animal symbols really did represent constellations. That is possible. Humans have looked at the sky and turned star patterns into animals for a very long time. But we do not have a Göbekli Tepe dictionary. No inscription tells us that a scorpion meant Scorpio, or that a bird represented a particular part of the sky. Second, we would need to know that the carvings were intended to record a precise date. Again, possible in principle, but not demonstrated. The people who made these images may have been recording myths, seasonal cycles, hunting symbols, ritual identities, dangerous animals, death, transformation or relations between the human world and the wild world. Third, there is the question of timing. The oldest layers at Göbekli Tepe are extraordinarily ancient, but they still date to around the end of the Younger Dryas and the beginning of the warmer Holocene, not securely to the moment a proposed impact would have occurred. Even if Pillar 43 contained a memory of an earlier catastrophe, we would have to explain how that memory was preserved accurately across many centuries, perhaps longer, before being carved into stone. That is not impossible, but impossible and proven are not the same thing. The compelling archaeological fact is that Göbekli Tepe reveals cultural complexity at a stunningly early date. People without cities, metal, writing, or domesticated grain on a large scale were capable of building monuments whose meanings were rich enough to remain partly mysterious 11 millennia later. The highly interpretive claim is that those monuments encode a global celestial disaster. Göbekli Tepe does not prove that a lost civilization existed before the Younger Dryas. It does not prove that survivors of a vanished high-tech culture taught later hunter-gatherers astronomy. And it does not prove that the Vulture Stone is a Stone Age disaster report. What it does prove is almost as fascinating. Human beings at the edge of the agricultural revolution were already capable of preserving ideas across generations. They could gather around shared symbols. They could build for purposes larger than immediate survival. They could look at animals, death, the seasons, the heavens, and the uncertainty of the world, then turn all of it into ritual. And that raises a question we cannot dismiss so easily. If people can preserve meaning in stone for 11,600 years, what else might they preserve in stories? Maybe they could preserve more than meaning. Maybe, under the right conditions, a story can carry a real piece of landscape through time. That sounds impossible at first. We are used to thinking of oral traditions as fragile things. A story gets told around a fire, then retold, then changed. Details drift, characters merge, gods appear, monsters appear. A real flood becomes a flood sent by the spirits. A volcanic eruption becomes a battle between ancestors. After enough generations, surely the original event disappears completely. Sometimes it does, but oral traditions are not just random stories passed from person to person, like a game of telephone. In many societies, they are systems of knowledge. They preserve migration routes, family relationships, hunting territories, water sources, seasonal cycles, sacred places, and rules for surviving in dangerous environments. For people without maps, a song can be a map. For people without written records, a genealogy can be a timeline. For people living in a landscape full of hidden hazards, a story can be a warning label that survives longer than any individual memory. Indigenous Australian traditions offer some of the most intriguing examples. Australia has been inhabited for at least 50,000 years, probably longer, and many Aboriginal communities maintained extraordinarily detailed systems of oral knowledge tied to specific places. Songlines could encode routes across enormous distances. They could identify water holes, edible plants, rock formations, boundaries, and ceremonial sites. To outsiders, they might sound like mythic journeys undertaken by ancestral beings. But for the people who carried them, they could also function as practical geographic knowledge. And some of these traditions may describe coastlines that no longer exist. At the end of the last ice age, sea levels rose by more than 120 metres. Vast areas of what had once been dry land disappeared beneath the ocean. Northern Australia was connected more closely to New Guinea. Tasmania was joined to the mainland. The coastlines were radically different from those people know today. A number of Aboriginal stories describe land being swallowed by the sea, islands separating from the mainland, and old travel routes vanishing beneath rising water. Researchers have argued that some could preserve memories of post-glacial sea level rise from 7, 8, maybe even more than 9,000 years ago. That would be astonishing, not because every detail would remain unchanged. It wouldn't. The stories may have been reshaped many times, but the central memory could survive. There used to be land there. People crossed it. Then the sea came in. There are other possible cases. In the Pacific Northwest of North America, several indigenous traditions describe a night when the ground shook. The sea rose, villages were destroyed, and the coast was transformed. Some researchers have compared these accounts with geological evidence for the Great Cascadia earthquake and tsunami of 1700 CE. That event is recent enough, historically speaking, to make the connection plausible. Japanese records independently document a mysterious orphan tsunami arriving across the Pacific at the same time. Then there is Mount Mazama in Oregon. Nearly 7,700 years ago, the volcano erupted catastrophically and collapsed, eventually forming Crater Lake. Klamath traditions tell of a conflict between powerful beings associated with the world above and the world below, ending in fire, destruction, and the collapse of a mountain. It is tempting to see the eruption inside that story. Maybe it is, but this is where we have to slow down. A tradition can align with a geological event without being a literal eyewitness report. A volcanic story does not automatically date back to a specific eruption. A flood story does not automatically describe one particular flood. Mountains erupt, rivers overflow, coastlines change. Fires fall from the sky, in the form of meteors, lightning, burning forests, and volcanic ash. Human beings everywhere have had reasons to create stories about these things. And the problem gets harder the farther back we go. Writing can preserve exact wording. Oral tradition preserves something different. It preserves patterns. It preserves memorable images. It preserves the emotional shape of an event. The water rose. The darkness came. The old world ended. A few people survived, and the rules of life changed afterward. But how do you date that original form? You can't simply ask when the story was first told, because no one wrote it down at the beginning. The earliest written version may be thousands of years younger than the story itself. Or it may represent a recent version of an older theme shared by many cultures. Stories travel with trade, migration, conquest, marriage, and religion. A myth recorded in one place may have absorbed elements from half a dozen others. This means we need a careful framework. First, does the story describe a specific local landscape? Not just the world flooded, but a particular island, river valley, mountain, or drowned coastal plain. Second, does geology show that something dramatic really happened there? Third, are there multiple independent traditions in the region that preserve similar details? And are those details unusual enough to be meaningful rather than universal human imagery? Finally, does the tradition fit the event without requiring us to force every symbol into a modern scientific interpretation? That last part matters most. We should not dismiss myths as nonsense just because they contain gods, monsters, talking animals, or impossible transformations. Myth is not failed science. It is a different way of organizing experience. It translates danger, loss, survival, and moral order into forms that people can remember. But we should not treat myth as a hidden newspaper either. A flood myth is not automatically evidence for Lake Agassiz. A fire from the sky story is not automatically evidence for a comet impact. A tale of darkness is not automatically proof of a global catastrophe 12,900 years ago. Still, the possibility remains. The Younger Dryas began in a world where human communities already had language, ritual, kinship networks, and long memories of place. If a generation watched climates shift, animals disappear, rivers change course, or coastlines drown, they would have had every reason to tell their children, and those children would have had every reason to keep telling it, not as a scientific report, as a warning. And nowhere is that possibility more tempting or more difficult to untangle than in humanity's oldest and most widespread disaster stories. The stories of the flood stories are everywhere. In Mesopotamia, they appear in some of the oldest written texts humanity ever produced. The gods decide to destroy mankind with a flood. One man is warned. He builds a great boat. He gathers his family, animals, seeds of life. The waters rise. The old world disappears. Then, after the flood, the survivors emerge into a world that has been reset. The names change. In the Epic of Gilgamesh, the survivor is Utnapishtim. In the earlier Atrahasis story, he is Atrahasis. In the biblical tradition, he is Noah. But the basic pattern is familiar. A warning, a vessel, a flood, survival, a new beginning. Around the Mediterranean, Greek mythology tells of Deucalion and Pyrrha, two survivors of a flood sent by Zeus. In South Asia, the ancient story of Manu describes a man warned by a fish that a great flood is coming. He builds a boat, survives, and helps restore life afterward. In parts of the Americas, flood traditions describe waters covering the land, people escaping to mountains, or a small group surviving in a canoe, raft, or hollowed tree. Across Oceania, stories speak of islands breaking apart, coastlines vanishing, and seawater advancing across country where people once walked. It is tempting to hear all of this and imagine one event. One unimaginable global flood, remembered by every culture on Earth. But that is almost certainly too simple. The flood myths of the world are not identical. They have different characters, different causes, different landscapes, different meanings. Some are about divine punishment. Some are about the creation of a new people. Some are about a local river overflowing. Some are about the sea taking land. Some may have spread from one culture to another through trade, migration, conquest, and religious contact. A story written down in Mesopotamia does not prove that people in the Pacific were remembering the same disaster. But that does not make the stories meaningless, because after the last ice age, the world really did flood. Not in a single week, not with every mountain swallowed beneath one universal ocean. but slowly, relentlessly, and sometimes catastrophically, over thousands of years. At the height of the last glacial period, so much water was locked up in continental ice sheets that global sea level was more than 120 meters lower than it is today. That is nearly 400 feet. Places that are now seabed were once coastal plains, river valleys, grasslands, hunting grounds, and migration routes. The Persian Gulf was largely dry land. The North Sea contained a huge lowland plain, now called Doggerland, connecting Britain to continental Europe. Southeast Asia was part of a vast exposed landmass called Sunderland. Australia, New Guinea and Tasmania were connected by broader stretches of land and shallow sea. Along every continent, shorelines stood miles, sometimes hundreds of miles beyond their modern positions. For people living there, the coast was not a line on a map. It was home. Then the ice melted. Sometimes the sea crept forward gradually, generation by generation. A child could walk across land where, centuries later, their descendants would travel by boat. A freshwater marsh became a tidal lagoon. A hunting ground became an island. A river mouth widened into an estuary. Eventually, villages, campsites, burial places, and old paths disappeared under salt water. That kind of change does not need to happen in one dramatic moment to become mythic. Imagine elders telling children that beyond the waves lies country their grandparents once knew. Imagine being warned not to forget the old route, even though no one can walk it anymore. Imagine watching the sea take another stand of trees, another freshwater spring, another piece of the world your people thought would last forever. That is exactly the kind of experience a culture would remember, and in some places the flooding may not have been slow at all. Glacial lakes could fail catastrophically. Ice dams could collapse. Rivers swollen with meltwater could tear through valleys, carrying mud, trees, animals, and boulders downstream with a force no human community could resist. Coastal earthquakes could generate tsunamis that arrived without warning, turning the sea itself into a moving wall. Volcanic eruptions, landslides, hurricanes, and storm surges could produce local disasters later woven into larger sacred stories. Mesopotamia, for example, sits between the Tigris and Euphrates, rivers capable of devastating floods. A massive regional inundation could easily have felt like the end of the entire world to people whose world extended only as far as the horizon, the river plain, and neighbouring settlements. In the Mediterranean, the collapse of coastlines, earthquakes, and tsunamis offered plenty of raw material for stories of sudden destruction. In South Asia, monsoon rivers could transform enormous areas into inland seas. In the Americas, communities living near glacial lakes, major river systems, and unstable coasts faced their own versions of watery catastrophe. Across Oceania, rising seas literally redrew the map beneath people's feet, so the similarities between flood traditions may not require one worldwide flood. They may reflect something more basic, and in some ways more haunting. Human beings kept living in places where water could erase the familiar world. And during the transition out of the Ice Age, that happened on a planetary scale. Not one flood, millions of local floods, thousands of drowned valleys, entire coastal landscapes gradually removed from human memory, except perhaps in stories. This is why submerged archaeology matters so much. For most of archaeological history, researchers search the land. That makes sense. Land is where we can dig. But the people of the late Ice Age did not live only on the land that remains above sea level today. Many would have lived near coasts, rivers, wetlands, and productive lowlands that are now underwater. Their settlements may be beneath the North Sea, beneath the Persian Gulf, beneath the seas of Southeast Asia, beneath drowned shelves around Australia, the Mediterranean, and the Americas. The absence of ruins on modern coastlines does not mean those places were empty. It may mean the evidence is underwater, and if communities watch those landscapes disappear, their descendants may have carried forward a stripped-down memory of what happened. Not the exact shoreline, not the exact date, not a scientific explanation of melting ice sheets and rising oceans, just the essential truth. There was land there once. The sea came, and the world was never the same again. But water is only one way the sky and earth can turn against you. Across the world, ancient stories also speak of fire falling from above, stars dropping from heaven, a sun that disappears, a sky turned black, smoke, ash, thunder, poisoned air, long darkness, and a world left broken after the flames. And this is where the Younger Dryas story becomes especially tempting. Because if a cosmic impact really did happen around 12,900 years ago, you might expect it to leave more than a thin layer of unusual material in the ground. You might expect it to leave a mark on human memory. A story passed from parent to child, generation to generation, until the details changed, but the terror remained. Something came from the sky. The world burned. Then darkness came. It sounds familiar because those images appear again and again in mythology. In Greek tradition, Phaethon loses control of the chariot of the sun and scorches the earth before Zeus strikes him down. In many cultures, falling stars are not distant rocks. They are omens, weapons, messengers, or beings crossing between worlds. Some traditions describe a former age ended by fire. Others describe darkness lasting longer than it should, the sun swallowed, hidden, or destroyed. Still others tell of a great battle in the heavens, followed by chaos on earth. To modern ears, these can sound like eyewitness accounts of a comet impact. But that leap is much larger than it first appears. Because human beings have always lived under a dramatic sky. And the natural world has many ways of producing the same language. A brilliant meteor can tear across the atmosphere in seconds, brighter than the full moon, leaving a glowing trail and a sonic boom that arrives after the light. A large bolide can explode in the air with the force of a weapon, lighting up the horizon, rattling the ground, and showering fragments across the landscape. People who saw the Chelyabinsk meteor over Russia in 2013 described a flash so intense it cast shadows. Windows shattered miles away. For a few moments, it must have felt like the sky itself had detonated. Now imagine seeing something like that without any knowledge of asteroids, atmospheric shock waves, or orbital mechanics. You would not say a rocky body entered the atmosphere at tens of thousands of miles per hour. You would say the heavens sent fire. An eclipse can do something similar. The sun dims in the middle of the day, birds fall silent. Temperature drops, shadows become strange. For people who do not know what is happening, the disappearance of the sun is not an astronomical event. It is a crisis in the structure of reality. Something has taken the light. Something has broken the order of the world. Volcanoes can produce darkness even more literally. A major eruption can blast ash high into the atmosphere, turning day into twilight, coating fields, contaminating water, and causing roofs to collapse beneath the weight of ash. Lightning flashes through black clouds. The ground shakes. Mud flows race down valleys. In the worst cases, people can watch a mountain explode and then spend months or years living beneath a dimmed sky. Wildfire creates its own version of apocalypse. Dry forests ignite. Smoke turns noon orange or black. Ash falls like snow. Animals flee. Familiar landmarks vanish behind a wall of flame. A community surrounded by fire does not need a comet to tell stories about a burning world. Neither does a violent storm. Thunder is already the voice of gods in countless traditions. Lightning is a weapon. Wind is a living force. A hurricane, cyclone, or dust storm can darken the sky, uproot forests, flatten homes, and transform an ordinary landscape into something unrecognizable. In the aftermath, survivors are left with exactly the kind of emotional raw material from which myth is made. So, when we find a story about fire from the sky, darkness at noon, or stars falling to earth, what have we found? We have found a powerful story that matters, but it is not the same thing as finding a confirmed impact crater dated to 12,900 years ago. This is the line that has to remain clear. Myths can preserve real experiences. They may carry memories of eruptions, floods, earthquakes, tsunamis, fires, unusual celestial events, and landscapes lost to rising seas. Oral traditions can sometimes transmit information for astonishing lengths of time, especially when that information is tied to place, ritual, law, and survival. But myths do not arrive as untouched recordings from the past. They are retold, reinterpreted, combined with other stories, adapted to new religions, new rulers, new landscapes, and new fears. A fire from heaven can become a lesson about pride. A flood can become a warning against corruption. A darkened sun can become a sign that kings have failed, that ancestors are angry, or that the moral order has been violated. That is what myth does. It takes catastrophe and gives it meaning. And the meaning is often more important to the people telling the story than the physical event that may have inspired it. A ruler may use a destruction story to explain why a new dynasty has the right to rule after the old world failed. Priests may use it to reinforce ritual obligations. Elders may use it to teach children where not to travel, which season to fear, or why certain places are sacred. A disaster becomes more than an event. It becomes a map for living. That is why trying to force every ancient story into the shape of a Younger Dryas impact can actually make the stories less interesting. It treats them like damaged scientific reports waiting for us to decode them. But they are not reports. They are cultural memory, moral instruction, sacred history, and sometimes perhaps a distant echo of something real. The physical evidence still has to carry the historical claim. If a comet or asteroid triggered continent-scale wildfires, abrupt cooling, and the collapse of ecosystems across the Northern Hemisphere, scientists need evidence that can be measured, dated, tested, and independently reproduced. They need impact markers that appear in the right places at the right time. They need a mechanism consistent with the geology, the climate records, and the archaeological record. They need more than a compelling resemblance between a cosmic hypothesis and a story about a falling star. Stories can suggest questions. They cannot settle them. Still, there is something worth holding on to here. At the end of the Ice Age, people lived through a world of melting ice sheets, changing rivers, rising seas, violent storms, burning landscapes, and sudden climate shifts. They watched places disappear. They saw animals vanish. They endured events that would have seemed impossible until they happened. Whether or not any myth remembers a single Younger Dryas catastrophe, ancient people had every reason to imagine that the world could end in water, fire, darkness, or ice, and perhaps that is the deepest connection, not proof of one lost event. But the memory of living on a planet capable of changing faster than human beings expect. That may be the real lesson of the Younger Dryas. Not that we have discovered a single lost day when a comet struck, civilization vanished, and the survivors carried one perfect memory of the disaster through 12,000 years of storytelling. The evidence does not support that kind of neat ending. What it supports is, in some ways, more unsettling. Around 12,900 years ago, the climate system changed with extraordinary speed. In the North Atlantic region, temperatures plunged back toward near-glacial conditions after the warming that had begun the end of the last ice age. Ice cores from Greenland preserve that reversal with astonishing clarity. Lake sediments, pollen records, cave deposits, and ocean cores show that the shift was not confined to one valley or one culture. It was part of a major reorganization of the climate system. Then, roughly 1,200 years later, the cold phase ended almost as abruptly as it had begun. That much is real, that much is written into the planet itself. But why it happened remains one of the most important unresolved questions in late Ice Age science. The leading explanation involves the Atlantic Ocean. As the great ice sheets melted, immense volumes of fresh water entered the North Atlantic. Fresh water is less dense than salty water. Add enough of it in the wrong place, and you may weaken the circulation that carries warm surface water northward and helps shape climate across the entire region. It is a massive planetary engine, and like any engine, it depends on balance. Heat moving north, cold water sinking, deep currents returning south. Ocean and atmosphere working together in a system so large that it is easy to imagine it as permanent. But it was not permanent. The Younger Dryas is evidence that climate can have thresholds. Push a system gradually for long enough, and the response may not be gradual at all. The world can absorb change, absorb change, absorb change, and then suddenly reorganize. That does not mean every climate shift is caused by one dramatic trigger. It does not mean we can point to the Younger Dryas and predict an identical event tomorrow. The Ice Age world was different from ours. There were enormous ice sheets across North America and Northern Europe. Sea levels were far lower. Coastlines were in different places. The amount of meltwater entering the oceans and the pathways it followed were unlike anything in the modern world. But the basic warning remains. Earth's climate is not a thermostat that moves smoothly 1 degree at a time. It is a network of oceans, ice, forests, winds, clouds, rivers and living systems. Change one part of the network, and the effects can travel outward in ways that are difficult to predict. A weakened current can alter rainfall. Altered rainfall can shift grasslands and forests. Shifting ecosystems can transform where animals live, where people can hunt, where crops can grow, and which societies can survive. For mobile hunter-gatherer communities at the end of the Ice Age, these changes were not abstract graphs on a scientific report. They were hunger. They were familiar migration routes no longer producing game, rivers changing course, wetlands drying out or expanding, winters becoming harsher, springs arriving late, herds moving beyond reach, coastlines advancing inland, taking campsites, fishing grounds, burial places, and entire landscapes beneath the sea. A society does not need to be technologically primitive to be vulnerable to environmental shock. It only needs to be dependent on systems it cannot control. And that is true now as much as it was then. Modern cities are not small camps beside a glacial river. We have satellites, reservoirs, global trade, weather forecasts, medicine, engineering, and more stored knowledge than any previous civilization could imagine. But we are also connected on a scale no Ice Age community ever experienced. Food grown in one region feeds people thousands of miles away. A drought, flood, heatwave, or failed harvest can move through markets and supply chains long before it arrives at anyone's doorstep. Complexity gives us strength. It can also create new kinds of fragility. That is why the Younger Dryas matters, not because it proves that humanity was reset by a cosmic apocalypse, but because it shows that stable conditions can disappear. It shows that environmental change can be fast enough to outrun expectations. And it shows that the people who survive are not always the strongest in isolation. They are often the people with options, diverse food sources, flexible social networks, shared knowledge, the ability to move, adapt, cooperate, and remember. And what about the impact hypothesis? What about the black mats, the microspherules, the platinum anomalies, the reports of widespread fire, and the possibility that something from space helped push an already unstable world into crisis? Those questions remain open to investigation. Some researchers continue to argue that the evidence points toward a fragmented comet or other cosmic event. Others find the proposed markers inconsistent, poorly dated, or explainable through terrestrial processes. No confirmed crater has settled the debate. No single line of evidence has forced universal agreement. That uncertainty is not a failure of science. It is science doing the harder thing. It is refusing to turn an intriguing possibility into a fact before the evidence can carry the weight of the claim. Archaeology does something different, but equally important. It asks how real people lived through this unstable age, how they changed their tools, their hunting strategies, their settlements, their trade networks, and their relationships with the landscape. It does not need one universal catastrophe to recognize disruption. A changing climate can reshape human life unevenly, region by region, generation by generation. And myth asks another question entirely, not simply, what happened? But what did catastrophe mean? What did people fear? What did they owe one another after the waters rose, the animals disappeared, or the sky turned dark? How did communities transform loss into a story that could be remembered? A flood myth may not tell us the exact date of an ancient inundation. A tale of fire from heaven may not identify a comet. But both can reveal something true about human beings living with forces beyond their control. Science measures the ice. Archaeology uncovers the camps, tools, bones, and buried landscapes. Myth preserves the feeling of standing in a changing world and trying to explain why it changed. None of these by themselves gives us the whole story. Together they remind us that the past is not a puzzle designed to produce one satisfying answer. Sometimes the honest answer is a map of what we know, what we suspect, and what still waits beneath the ice, under the sea, or inside sediments no one has studied yet. The Younger Dryas was not a proven global reset, but it was a real climatic shock during a period when human worlds were already changing at breathtaking speed. And maybe that is enough to make it unforgettable. So was the Younger Dryas a reset? In one sense, yes. Not a proven reset of all human civilization, not a confirmed single day when the whole world burned, but a real reset in the older, harsher meaning of the word. A period when familiar patterns broke down, when warming gave way to cold. When waters moved, ecosystems shifted, animals disappeared from parts of the world, and human communities had to adapt to landscapes that no longer behaved the way they once had. Around 12,900 years ago, the planet did something extraordinary. It reversed course. The last ice age seemed to be loosening its grip. Then, especially across the North Atlantic, cold conditions returned with startling speed. For roughly 1,200 years, the world entered another chapter of instability before warming resumed and the Holocene, the relatively stable climate age in which civilization developed, truly began. The leading explanation is not mysterious in the supernatural sense. It is meltwater. Vast amounts of fresh water from collapsing ice sheets may have disrupted the Atlantic circulation system, weakening the transport of heat northward. A slow process of ice melt may have triggered a rapid response from the climate machine. But the impact hypothesis remains unresolved. Some evidence has been interpreted as signs of a cosmic event. Other researchers argue those signals are inconsistent, uncertainly dated, or produced by ordinary Earth processes. It is possible that future discoveries will clarify the case. It is also possible the final answer will be more complicated than either side expects. And then there are the extinctions, the changing stone tools, the disappearance of Clovis traditions, the drowned coastlines, and the ancient stories of floods, darkness, fire, and renewal. These questions connect, but they are not the same question. Extinctions have fossil evidence. Cultural change has archaeological evidence. Climate reversal is preserved in ice, mud, pollen, and ocean sediment. Myths preserve something different, the human memory of living in a world where nature could become terrifyingly unpredictable. They may contain echoes of real environmental disasters. But stories alone cannot date an event, identify a comet, or settle a scientific debate. What they can do is remind us that people have always known something modern societies sometimes forget. Stable worlds can change faster than human expectations. That is the warning, and that is why this mystery still matters. If you enjoyed this journey into the Younger Dryas, please like the video, subscribe, and share your thoughts below. Where are you listening from? And what does this story make you think about in your own landscape? And if you want to support the channel in the best possible way, listen on Spotify using the link in the description.